This is TOI-700d, a planet orbiting a tiny crimson sun just 100 light-years away. Hidden within the constellation Dorado, emitting only a fraction of the sun's light. It's almost the size of Earth. Discovered by NASA's TESS mission, this world may be small, but it could be our best chance yet at finding life beyond Earth. The discovery of TOI-700d. Red dwarfs are the most common stars in the galaxy. Small, cool, and long-lived, but often unpredictable, prone to violent flares that can strip planetary atmospheres. TOI-700, however, displayed a rare calm. The discovery began in 2018, when NASA's Transiting Exoplanet Survey satellite, TESS, trained its instruments on this quiet star. TESS uses the transit method, detecting the subtle dimming of starlight when a planet crosses the star's face. During the initial observations, the satellite recorded 3 distinct patterns of dips in brightness, suggesting 3 planets orbiting TOI-700. At first glance, these signals seemed unremarkable. The star itself, however, had been mischaracterized. Early catalogues overestimated its size and temperature, which, in turn, inflated the perceived size and heat of its planets. Worlds initially dismissed as inhospitable suddenly required a closer look. Reanalysis of stellar data revealed that TOI-700 is smaller and cooler than first thought. Its radius is roughly 42% that of the Sun, with a surface temperature just over 3000 Kelvin, and its luminosity barely exceeds 1% of the Sun's output. The innermost planet, TOI-700b, remained a hot, rocky world with a 10-day orbit. The middle planet, TOI-700c, a 2.6 Earth-radius planet, was likely gaseous or icy. The outermost planet, TOI-700d, however, emerged as the most striking. Orbiting every 37.4 days, it sits squarely within the star's habitable zone, the range where surface temperatures could allow liquid water. The Spitzer Space Telescope, observing in the infrared, played a decisive role. Spitzer captured multiple additional transits of TOI-700d, refining its radius and orbital period. The data confirmed that TOI-700d is approximately 1.14 times the radius of Earth and likely rocky. Its orbit places it in a region that receives roughly 86% of the solar energy Earth receives, suggesting temperatures that could permit temperate conditions. This discovery became one of the last major contributions of the telescope before it was decommissioned in 2020, a final act that extended its legacy in the search for habitable worlds. The discovery process involved collaboration across multiple institutions. Scientists at NASA's Jet Propulsion Laboratory, including Emily Gilbert, worked closely with teams at the Harvard-Smithsonian Center for Astrophysics, where Joseph Rodriguez contributed to refining the transit data and validating the planetary signals. Analysts combined TESS and Spitzer observations with models of stellar parameters, ensuring that the planet's size, orbit, and potential for habitability were accurately determined. TOI-700 days is remarkable not only for its location, but for the characteristics of its star. Red dwarfs often exhibit intense flare activity that can strip atmospheres from orbiting planets, but TOI-700's low activity level significantly increases the likelihood that its planet could maintain a stable atmosphere. The star's stability, combined with the planet's orbital position, makes TOI-700d a rare find. A rocky, Earth-sized planet in the temperate zone of a quiet M-dwarf. The planetary system is tightly packed but stable. TOI-700b, with a radius similar to Earth's, completes its orbit in just 10 days, receiving significantly more stellar energy than Earth, likely resulting in a scorched surface. TOI-700c, intermediate in size, is likely enveloped in a thick atmosphere, potentially a mini-Neptune or sub-Neptune type world. TOI-700d, the outer planet, occupies the sweet spot for habitability, with its 37-day orbit positioning it within the range where liquid water could persist, assuming a suitable atmosphere. Astronomers relied on combined light curves from TESS and Spitzer, analyzed with models of stellar luminosity, radius, and mass to determine precise planetary characteristics. Its Earth-like radius and orbit in the habitable zone made it the first Earth-sized planet discovered by TESS with temperate conditions, setting it apart from other exoplanets identified by the mission. TOI-700D's discovery demonstrated the importance of accurate stellar characterization. Initial misclassification of TOI-700 had obscured the planet's true potential. Once corrected, it transformed a modest TESS object of interest into one of the most promising candidates for habitability discovered to date. This underlines a broader principle in exoplanet research. The accuracy of stellar parameters is critical to understanding the planets that orbit them. The scientific significance of TOI-700D extends beyond its size and orbit. Its location in the habitable zone around a quiet red dwarf offers an accessible laboratory for studying planetary atmospheres and potential habitability. Unlike planets orbiting volatile stars like Proxima Centauri, TOI-700D is not subjected to frequent intense flares, making it a stable target for follow-up observations with the James Webb Space Telescope and other instruments designed to probe exoplanet atmospheres. Spectroscopic studies could reveal atmospheric composition, the presence of greenhouse gases, or the potential for water vapor, providing the first detailed characterization of an Earth-sized planet in a temperate orbit around a red dwarf. TOI-700D's discovery was also a milestone for TESS. Launched in 2018 with the goal of identifying nearby small planets orbiting bright stars, TESS had already catalogued thousands of potential exoplanets. However, TOI-700D represented a benchmark achievement, the first Earth-sized planet in the habitable zone confirmed by the mission. Its identification validated the satellite's observational strategies, demonstrating that TESS could detect small temperate worlds around faint, cool stars, not just large, hot planets around brighter stars. The confirmation process illustrates the technical rigor required for exoplanet science. Every transit signal must be scrutinized for false positives, such as background eclipsing binaries or instrumental noise. By combining multiple observations, carefully analyzing transit depths, durations, and periodicity, and cross-referencing with stellar models, astronomers established the planetary nature of TOI-700D beyond reasonable doubt. The resulting measurements of radius, orbital period, and incident stellar flux are among the most precise for any Earth-sized exoplanet discovered to date. TOI-700D also serves as a critical target for comparative planetology. Its rocky nature, temperate orbit, and stable star make it a natural laboratory to study planetary formation, evolution, and atmospheric retention around M-dwarfs. Models of tidal locking, climate dynamics, and potential water retention all find a real-world test case in this system. Unlike many exoplanets discovered around volatile red dwarfs, TOI-700D's relatively benign environment allows simulations of climate and atmospheric chemistry that can be compared directly with Earth-based models. The planetary system shows the diversity of exoplanets. TOI-700B's short orbit exposes it to intense stellar radiation, while TOI-700C represents a class of intermediate-sized planets whose composition is uncertain, possibly a water-rich world or a mini-Neptune. TOI-700D's temperate orbit contrasts sharply with its siblings, demonstrating how planets forming around the same star can occupy dramatically different environments. These contrasts provide valuable insights into planetary formation, migration, and the influence of stellar properties on planetary outcomes. TESS provided the initial detection. Spitzer confirmed the planet's existence and refined its size and orbital parameters, and ground-based follow-up observations helped rule out false positives. This layered approach shows the methodology of modern exoplanet discovery. No single instrument can provide a complete picture. Only through careful coordination, repeated observation, and precise modeling can planets like TOI-700D be reliably identified and characterized. TOI 700 days now stands as a cornerstone in the catalogue of potentially habitable exoplanets. Its radius, orbit, and stellar environment suggest conditions that could allow liquid water, making it one of the most promising targets for future studies. Unlike many Earth-sized planets around active red dwarfs, TOI-700d's calm host star increases the likelihood that it retains an atmosphere, a critical factor in evaluating habitability. The discovery provides an important data point for understanding how Earth-sized planets can form and survive around small, low-luminosity stars. In January 2020, the discovery was officially published, drawing global attention. Scientists emphasized the planet's potential, while noting that actual habitability depends on atmospheric composition and surface conditions, which remain unknown. Observational campaigns are now being planned with instruments capable of detecting atmospheric gases, climate patterns, and surface properties. TOI-700 days represents a tangible opportunity to study an Earth-sized world in a temperate orbit within reach of current and near-future observational technology. The discovery marked a turning point in exoplanetary science. TOI-700 days is not only one of the closest Earth-sized planets in the habitable zone around a quiet red dwarf, but also one of the first confirmed planets in such a position discovered by TESS. Its identification demonstrates the power of precision photometry, the importance of accurate stellar characterization, and the necessity of cross-instrument verification. This system offers a unique opportunity to study the physics of small planets, the dynamics of multi-planet systems, and the interactions between planets and low-luminosity stars. TOI-700d's orbit, size, and stellar environment collectively make it a model case for studying planetary habitability around red dwarfs. Its discovery confirms that small temperate planets can exist in the habitable zones of low-mass stars, opening new avenues for exploration. As one of the first Earth-sized planets confirmed in the habitable zone by TESS, it sets the stage for future missions to characterize atmospheres, assess climate dynamics, and search for chemical signatures indicative of surface conditions. The physical characteristics of TOI-700d. TOI-700 days has a radius about 1.14 times that of Earth, a subtle difference, almost imperceptible, but enough to affect its gravity, atmosphere, and potential geology. Its mass, estimated at roughly 1.25 Earth masses, suggests a rocky composition, a solid surface beneath an atmosphere that might cling just as tightly as ours does. It orbits its star at 0.163 astronomical units, roughly 1/6 the distance between Earth and the Sun. While this may seem small, the star itself is only a fraction of the Sun's size and luminosity. That closeness positions TOI-700 perfectly within the habitable zone, where the energy it receives from its star is roughly 86% of what Earth receives from the Sun. That energy is critical. It determines the potential surface temperature, the climate dynamics, and whether water, if present, could remain liquid. Models suggest that depending on the atmosphere, surface temperatures could range from 268 to 295 Kelvin, or roughly 5 to 22 degrees Celsius. Not unlike our planet, but under a sky perpetually tinged red, where sunlight carries less intensity but more persistence. But the first striking difference from Earth is day and night. TOI-700 days is most likely tidally locked, a common fate for planets orbiting small stars in close proximity. Tidal locking occurs when gravitational forces synchronize a planet's rotation period with its orbital period, resulting in the same hemisphere always facing its star. Imagine a world where one side bakes in eternal sunlight, while the other lies in endless, frigid darkness. Across the planet, this creates dramatic contrasts. The day side could harbor scorching temperatures near the substellar point, while the night side plunges into near-freezing cold. Between these extremes lies a narrow, elongated band known as the terminator, the twilight zone where day meets night. It is here, along this ring, that temperatures might be most stable, where winds, atmospheric circulation, and radiation could converge to create regions hospitable to liquid water. The mechanics of tidal locking are fascinating in themselves. Unlike Earth, which spins on its axis independently of its orbit around the Sun, TOI-700d has been gradually slowed by the gravitational pull of its star. Over millions of years, this pull synchronized rotation, stretching and compressing the planet slightly, generating heat through tidal friction. This subtle warming effect may prevent the night side from becoming an icy wasteland, redistributing energy through the planet's atmosphere if one exists. In essence, the same gravitational force that locks the planet's rotation also contributes to its climate stability, creating a delicate balance that makes its temperate zones possible. Observing the orbit, TOI-700d presents a remarkably stable path around its star. Unlike many red dwarfs, which emit frequent flares and radiation bursts that can destabilize planetary atmospheres, TOI-700 is unusually calm. Its low stellar activity reduces the risk of atmospheric stripping or radiation surges, allowing the planet's surface conditions to remain relatively consistent over long periods. The orbit itself is nearly circular, with low eccentricity, meaning the planet experiences minimal variation in stellar energy throughout its year. This is critical for the development of stable climates and weather patterns. On the day side, the sky is dominated by a deep, rusty red glow, far dimmer than our Sun, but persistent enough to illuminate rocky plains, potential oceans, and cloud patterns. The atmosphere, if present, scatters light differently than Earth's, giving the sky a reddish hue and tinting clouds with shades of rose or amber. The night side, in perpetual darkness, is a realm of frozen silence. Without stellar heat, surface temperatures plummet, and if there is water, it may exist as ice, locked in vast polar-like sheets, stretching toward the terminator, where it melts under the diffuse red sunlight. The twilight band is the most intriguing, a dynamic edge between extremes, where wind flows from hot to cold regions, clouds form along gradients, and the possibility of temperate conditions arises. Models of atmospheric circulation suggest that even modest winds could transport heat from the day side to the night side, moderating extremes and creating potentially stable environments along the terminator. The planet's energy budget is another area of interest. Receiving 86% of Earth's solar flux, TOI-700d is neither too dim nor too hot, but the spectrum of light differs. Red dwarfs emit most of their energy in the infrared. This shift affects surface heating, atmospheric chemistry, and photosynthesis, if any biological processes were present. Radiation that reaches the surface is less intense in the visible spectrum, favoring infrared-absorbing molecules and potentially altering the planet's weather patterns. Clouds, for example, may reflect differently, leading to distinct albedo effects compared to Earth. This spectral difference also influences planetary temperatures, as infrared light penetrates the atmosphere differently, potentially warming surfaces even under lower total energy flux. Tidal locking also affects planetary climate in less obvious ways. The day side, continuously exposed, may develop a strong substellar point where solar energy is concentrated at a near-permanent spot. Heat rises, generating convection currents, potentially forming large storm systems. The night side, devoid of direct heating, becomes a region where gases sink and cold air accumulates. Between these extremes, atmospheric circulation could establish jet streams along the terminator, moving heat from the sunlit side to the dark side, moderating temperature differences. For planets with oceans, this process could also drive currents, redistributing thermal energy, stabilizing climates, and creating narrow habitable regions along the twilight belt. Geological activity may also play a role. Tidal forces exerted by the star could induce stresses in the planet's crust and mantle, generating internal heating through friction. This tidal heating is subtle, but over millions of years it can drive volcanism, maintain a molten core, and support a magnetic field. A magnetic field, in turn, would shield the atmosphere from stellar winds and cosmic radiation, preserving its composition over geologic timescales. Without such protection, even a planet in the habitable zone could lose its atmosphere and water to space. The planet's orbit is remarkably quiet. Unlike planets around volatile red dwarfs, which often face intense flare activity, TOI-700d orbits a stable star, with minimal variations in luminosity and magnetic activity. This stability ensures predictable energy input, allowing surface conditions to remain relatively constant. The combination of a circular orbit, low stellar activity, and tidal locking creates a planetary environment dominated by extremes moderated by dynamic processes, a complex system that could support regions of relative temperance along the terminator. The gravitational interactions between TOI-700d and its star also maintain orbital stability across long periods. Red dwarfs are small but dense, exerting strong tidal forces on close-orbiting planets. TOI-700 days has likely reached equilibrium, its orbit and rotation locked in a steady rhythm. This equilibrium prevents the chaotic orbital variations that can affect climates and disrupt atmospheres on other exoplanets. Its neighbors, TOI-700b and c, do not significantly perturb its orbit, allowing it to maintain its 37-day year without dramatic changes in eccentricity or inclination. From a visual perspective, imagining TOI-700d from orbit is striking. The dayside glows dimly red but persistent, illuminating a world of potential rock, ice, and liquid water. The night side is a frozen expanse, black and silent, perhaps dotted with faint glimmers of ice reflecting distant starlight. The terminator, a crescent-shaped twilight zone, appears as a thin band of orange or amber light, where temperatures could be stable and dynamic weather patterns form. This region would likely host complex circulation, clouds forming and dissipating as winds shift heat from day to night, possibly producing precipitation along the gradient. The spectral quality of the star also impacts climate. Infrared radiation penetrates deeper into the atmosphere than visible light, potentially warming surface layers and oceans efficiently, even under a redder, dimmer sky. This may allow liquid water to persist in temperate regions, even with lower total energy flux than Earth receives. Additionally, the star's low flare activity ensures that any atmosphere is not stripped away over time, increasing the likelihood that surface or near-surface water could remain stable over geologic timescales. Tidal locking may also influence the planet's rotation-dependent weather patterns. Without the day-night cycle familiar on Earth, winds are dominated by the temperature gradient from the substellar point to the night side. The Coriolis effect would be weaker due to slow rotation, so storm systems could be broad and persistent, rather than compact and fast-moving like on Earth. Atmospheric modeling suggests that the terminator could host moderate winds, perhaps forming cloud belts that track the boundary between extreme day and night conditions. These winds may play a critical role in distributing heat and maintaining habitable regions along the twilight band. Ocean circulation, if present, would respond similarly. Water heated on the dayside would expand and flow toward cooler nightside regions, while colder water would sink and flow back, establishing global currents. Even modest tidal heating from gravitational interactions could drive internal warming, supporting active volcanism or a molten interior. Such activity would contribute to magnetic field generation, recycling of nutrients, and a dynamic surface environment, all factors relevant to the stability of potential habitability. TOI-700d's size and gravity are important for maintaining these systems. At roughly 1.25 times Earth's mass, its gravitational pull is strong enough to retain a dense atmosphere, resist erosion by stellar winds, and maintain liquid water over extended periods. Gravity also influences tectonics, volcanism, and atmospheric pressure, all of which determine climate stability. A planet too small would lose its atmosphere. One too large might develop a thick, hydrogen-rich envelope, preventing temperate surface conditions. TOI-700 days sits within this narrow window, making it a planet of exceptional interest. A quiet star in a violent galaxy. Among the stars scattered across the Milky Way, red dwarfs dominate. They are the galaxy's most common stellar residents, small and cool, quietly burning for trillions of years, far longer than the Sun's expected lifespan. Their diminutive size makes them faint, often invisible to the naked eye, yet their abundance is staggering. Anywhere we look in the galaxy, red dwarfs outnumber larger stars, quietly shaping the cosmic neighborhood. But for all their prevalence, red dwarfs are often hostile. Their small size and intense magnetic fields make them prone to violent outbursts. Frequent flares of high-energy radiation can erupt from their surfaces without warning, bathing orbiting planets in bursts of X-rays and ultraviolet light. These flares are not trivial. They are capable of stripping away atmospheres and sterilizing planetary surfaces. A world orbiting such a star, even within the so-called habitable zone, could be rendered uninhabitable almost instantly. Planets that might otherwise sustain liquid water can lose it to space, and life as we know it would struggle to survive. Red dwarfs, common as they are, often pose lethal challenges for planets in orbit. TOI-700, however, is an exception. Among the millions of red dwarfs in our galaxy, this star is unusually calm. Observations show low stellar activity and a remarkably stable output of energy. It emits a steady, gentle glow without the violent flares that characterize stars of similar size. For astronomers, this stability is a rare and vital trait. Planets around violent red dwarfs may never maintain stable climates or retain atmospheres. But TOI-700 offers a calm environment, a cosmic sanctuary amid a galaxy often hostile to small planets. The quiet nature of TOI-700 is critical for its planet, TOI-700d. Unlike planets orbiting hyperactive stars, TOI-700d is unlikely to face repeated sterilizing events. Its atmosphere, if it exists, is not constantly bombarded by high-energy radiation capable of stripping gases into space. The energy it receives from its star is consistent and predictable, allowing temperatures to remain relatively stable. In the habitable zone, that steady energy makes the difference between a world where liquid water can persist and one that remains frozen or baked away under extreme radiation. To understand the significance of TOI-700's calm, it helps to compare it with other well-known red dwarfs. Proxima Centauri, the closest star to our Sun, is an example of a volatile red dwarf. Its flares can increase brightness by factors of hundreds within minutes, unleashing torrents of radiation that sweep across orbiting planets. Proxima Centauri b, a planet in its habitable zone, exists under a constant threat of stellar violence. Models suggest its atmosphere could be stripped away over time, and any surface water would be vulnerable to intense radiation bursts. While its orbit may place it in a temperature range that seems potentially habitable, the star's volatility undermines that possibility. TOI-700, by contrast, operates with serene consistency. Its magnetic activity is low and flare frequency is minimal. Unlike Proxima Centauri, whose energetic outbursts dominate the environment of its planets, TOI-700 provides a stable backdrop, bathing TOI-700d in steady light. This stability is not just a convenience for astronomers modeling planetary climates, it is a fundamental requirement for habitability. Without the constant threat of atmospheric loss or radiation spikes, a planet can retain gases such as nitrogen, oxygen, or carbon dioxide, which are essential for regulating surface temperature and sustaining a stable climate. The implications for TOI-700d are profound. Orbiting at 0.163 astronomical units, it is close enough to its star to receive sufficient energy for liquid water, but far enough to avoid intense tidal heating that could destabilize its crust. The star's stability ensures that the energy received varies little over time, unlike the unpredictable bursts experienced by planets around flare-prone stars. This creates a relatively predictable environment where atmospheric dynamics, surface temperatures, and potential hydrological cycles can develop and persist. This serene environment allows us to imagine TOI-700d not as a planet constantly battered by its star, but as a world where energy input is regular and moderate. On the day side, The light is dimmer than Earth receives from the Sun, but it is steady, enough to warm rocky surfaces, maintain oceans if present, and drive atmospheric circulation. On the night side, the absence of stellar flares means that temperatures can stabilize rather than plunge unpredictably during bursts of radiation. The twilight zone between day and night, the terminator, is less likely to be exposed to catastrophic heating events, making it a prime candidate for stable climates and liquid water. The spectral output of TOI-700 also plays a role. As a red dwarf, its light is concentrated in the infrared, longer wavelengths than visible sunlight. Infrared penetrates planetary atmospheres differently, warming the surface without the intense ultraviolet component that can destroy molecules. For TOI-700d, this means that any atmosphere can retain heat more effectively, particularly along the terminator, where day and night meet. Models suggest that this can create a band of temperate climate encircling the planet, where winds distribute heat from the day side to the night side, smoothing extremes and preventing permanent freezing or overheating. Gravitational interactions further enhance stability. TOI 700 days is tidally locked, with the same side always facing the star. While tidal locking can create extreme temperature contrasts, the combination of steady stellar output and low flare activity mitigates the harshest consequences. The planet experiences a constant gravitational pull from its star, stretching its interior slightly but without catastrophic disruptions. This tidal influence may generate mild internal heating, supporting tectonic activity and possibly maintaining a magnetic field, which in turn shields the atmosphere from charged particles and cosmic rays. The comparison with violent red dwarfs highlights just how unusual TOI-700 is. Many planets around M-dwarfs are effectively exposed to a cosmic battering ram, with stellar flares eroding atmospheres and irradiating surfaces. Planets that might otherwise fall within the habitable zone often lose the very conditions needed for liquid water or stable climates. TOI-700d, by orbiting a calm star, avoids these destructive effects. Its atmosphere, if it exists, is likely retained over billions of years, its climate regulated by predictable energy input, rather than sporadic bursts of stellar violence. The serenity of TOI-700 also simplifies modeling potential climates. Without unpredictable flares, scientists can simulate atmospheric circulation, ocean currents, and weather patterns with higher confidence. Day-to-night heat transport, driven by winds along the terminator, becomes the dominant mechanism for energy redistribution. The result is a planet that could host regions of relative stability, where temperatures hover within a range compatible with liquid water. Clouds could form in the twilight zone, reflecting some infrared energy back to space while trapping warmth below, creating microclimates that are remarkably Earth-like, despite the alien spectrum of light. Even the planet's orbit contributes to this calm. Unlike planets around highly active stars, TOI-700d's nearly circular path means that energy input does not vary significantly throughout its 37-day year. There are no intense seasonal swings or episodic heating events caused by stellar activity. The combination of steady irradiation, low flare frequency, and tidal locking creates a stable environment where potential atmospheres are protected, climates can persist, and liquid water may remain on the surface for geologic timescales. This rare combination, Earth-sized planet, temperate orbit, and calm star, places TOI-700d among the most promising exoplanets for study. Its host star's serenity is not just a detail, it is central to the planet's potential habitability. The low energy variability ensures that atmospheric molecules are not stripped away, that water can cycle between surface and atmosphere, and that weather patterns can establish a persistent rhythm. In contrast, planets orbiting flare-active stars face dramatic swings in radiation, temperature, and atmospheric retention, making stable surface conditions extremely unlikely. From a visual perspective, imagining TOI-700d orbiting its gentle red sun evokes a sense of cosmic balance. The star glows with a consistent, deep crimson light, bathing the day side in warmth but never overwhelming it. The night side remains dark but is protected from destructive flares, allowing temperatures to stabilize rather than plunge unpredictably. Along the terminator, the balance of light and dark creates a narrow belt of temperate conditions, where atmospheric circulation and potential hydrological processes might converge. It is a planet shaped not only by its own properties, but by the rare serenity of the star it orbits. Even small variations in stellar activity would have profound effects. A violent flare could strip gases, disrupt climate patterns, or vaporize water. That TOI-700 rarely, if ever, produces such events is a significant advantage. It allows for the possibility that surface features, oceans, and atmospheric compositions remain consistent over millions or billions of years, unlike worlds orbiting more volatile red dwarfs. For exoplanet science, this is an invaluable opportunity, a relatively simple system where conditions can be modeled accurately, tested against observations, and studied in detail with future telescopes. TOI-700D's stability also extends to its interior and geological activity. Tidal forces from the star are constant and predictable, producing modest heating that may drive convection within the mantle. This energy source could support volcanic activity, cycling gases into the atmosphere, maintaining magnetic fields, and preventing complete surface freezing on the night side. Without a calm star, such internal processes might be overwhelmed by atmospheric stripping or radiation bursts. TOI-700 provides the quiet necessary for these geological systems to function and interact with the atmosphere over extended periods. Life in the twilight zone. Imagine a planet where the sun never rises and yet never sets, where one side bakes under eternal daylight while the other plunges into endless night. That's life on a tidally locked planet, and on TOI-700D, it's reality. The star never moves in the sky for half the planet. For the other half, darkness stretches infinitely. But between these extremes, a narrow glowing ribbon, the terminator line, offers a zone of balance, a place where day and night meet, and where conditions might actually resemble Earth. Tidal locking is not some distant theory. It's a physical consequence of the planet's close orbit around a small star. Gravity has done its work over millions of years, slowing the rotation until the same side always faces the star. It's a cosmic dance frozen in place. The side pointed at TOI-700 receives constant, gentle light, a red-tinted noon stretching forever. Geologists call this the substellar point. Here the heat never fades, skies glow in dim crimson, and if oceans exist, they simmer without respite. The air here moves differently than Earth's. Hot air rises continuously, driving convection patterns that never pause. Storms could form and linger for months, even years, swirling around the substellar point like a giant atmospheric wheel. Move away from that eternal noon, and the planet's surface changes rapidly. The red light fades into darkness, the heat drops, and the air cools as it flows toward the night side. Winds along this gradient can be violent. On Earth, a day lasts 24 hours, giving air masses time to move slowly and weather patterns to stabilize. On TOI-700D, air is constantly on the move. Hot air from the substellar point rises, cools as it drifts toward the dark side, and sinks, creating persistent wind belts along the terminator line, the twilight ring where life-friendly conditions might exist. This twilight zone is the star of the show. Here, temperatures could be mild, hovering somewhere between the frozen night side and the burning day side. Models from NASA Goddard show that if TOI-700D has an atmosphere, even a thin one, this region could maintain stable temperatures, potentially allowing liquid water to persist. It's not uniform like Earth. Instead, the climate may be patchy, with micro-regions of warmth and cool swirling winds, clouds forming along the line where day meets night, and maybe even rain. Imagine standing on the terminator. To one side, the sky is painted in permanent sunset, a deep crimson glow spreading over jagged terrain, maybe oceans glinting like molten copper. On the other side, darkness stretches into a starless void, cold and still, with icy plains that never melt. The horizon is a band of deep orange and amber light, where wind carries warmth from the day to the night. Clouds drift in long streaks, and temperatures might stay within the range life could tolerate. This is not science fiction. It is the real physics of a tidally locked world. The substellar point is fascinating in its own right. Here, the light from TOI-700 is steady, never waxing or waning. The energy input is roughly 86% of what Earth receives from the Sun, but distributed differently. The peak heating occurs at the center of this eternal noon, tapering off as you move outward toward the twilight zone. The heat drives continuous convection in the atmosphere. Clouds could form, persist, and dissipate over years rather than hours. Surface features like rocks or oceans receive unbroken radiation, slowly warming to a near constant temperature. If water exists, it could evaporate steadily, feeding the winds that carry heat toward the dark side. On the night side, conditions are harsh. Without sunlight, temperatures could drop below freezing, turning any water into ice. Atmospheric circulation is critical here. Winds from the day side may prevent the night side from becoming an endless ice desert, especially along the twilight zone. Even a modest atmosphere could distribute heat efficiently, smoothing temperature extremes. But if the planet lacks sufficient gases, the night side might be inhospitable, frozen, and barren. The key, then, is the twilight belt, a narrow ribbon where physics and climate combine to create a potential sweet spot for habitability. Simulations suggest this region is dynamic. Clouds may cluster along the terminator, forming long horizontal bands that drift slowly. The winds carry warmth across the boundary, creating eddies, turbulence, and possibly rain cycles. Precipitation might fall in patterns entirely unfamiliar to us, feeding shallow seas or rivers in permanent sunset. Life, if it exists, would have adapted to these unique conditions, thriving in a climate dictated by unending contrast. Heat from one side, cold from the other, winds carrying water, and light filtered through a crimson sky. The substellar point and the terminator are not static. The boundary shifts slightly due to topography, atmospheric pressure, and heat transport. Volcanoes, mountains, or oceans could bend winds, redirect clouds, and influence local climates. Unlike Earth, where rotation spreads day and night evenly, the unchanging orientation creates long-term patterns. Storms may last years rather than hours, and winds may carve landscapes differently than anything on our planet. The constant push and pull of heat and cold may produce unique weather phenomena: spiraling clouds above the substellar point, ice fog along the night boundary, and gusts sweeping along the twilight ring. These patterns are not purely theoretical. NASA's Goddard climate models simulate atmospheres on tidally locked planets like TOI-700d. They predict that if the planet has even a modest mix of nitrogen and carbon dioxide, the terminator can maintain stable conditions suitable for liquid water. Heat from the day side flows into the night side, preventing permanent freezing, while the night side's cooler air flows back toward the day side, moderating extremes. This circulation creates what scientists call a permanent climate belt along the terminator, a zone where liquid water could exist in lakes, rivers, or even shallow seas. The length and width of this belt depend on atmospheric density. A thin atmosphere leads to a narrow zone, perhaps only a few hundred kilometers wide. A denser atmosphere could extend it across thousands of kilometers, increasing the habitable area. Winds, convection, and cloud formation all interact in complex ways. Along the boundary, clouds could cast shadows, reducing local heating, while fog could trap warmth from the day side, maintaining surface temperatures. These microclimates are completely alien, but potentially life-sustaining. Gravity also influences climate patterns. TOI-700d's slightly higher mass than Earth increases surface gravity, helping retain the atmosphere. This stronger pull allows air and water to circulate efficiently, reducing loss of gases to space. The atmosphere, in turn, moderates heat transfer between the hot substellar point and the frozen night side. Combined with the star's calm output, this gravity-atmosphere relationship is key for maintaining stable conditions along the twilight zone. Waves in potential oceans would behave differently too. On Earth, tides are largely driven by the Moon, but on a tidally locked planet, gravitational pull from the star dominates. Oceans might bulge slightly toward the substellar point, creating permanent tidal pools or seas along the terminator. Surface water could evaporate steadily on the day side and condense along the twilight line, feeding rivers or lakes in continuous circulation. These constant processes would shape a landscape unlike anything on Earth. A world defined by contrasts, with liquid water existing only where the physics of light, heat, and wind align. The substellar point might be inhospitable for life as we know it. Temperatures could be high, clouds dense, and winds violent. But just a few hundred kilometers away, along the terminator, conditions mellow. Here, warmth from the day side and cooling from the night side balance out. Clouds drift lazily, winds are moderate, and surface temperatures could remain within a range tolerable for organisms similar to those on Earth. In other words, the planet's most promising real estate for life is not in perpetual noon or eternal night, but in the narrow, glowing ring where extremes meet. Scientists also note that tidal locking may stabilize the planet's rotation over time. Unlike Earth, where chaotic weather patterns sometimes produce extreme variations, the constant orientation on TOI-700d could allow predictable winds and persistent cloud belts. Climate cycles might operate over decades rather than hours, giving potential ecosystems time to adapt. Life, if it exists, would have evolved in a world where sunlight is never fleeting and darkness never ends, an alien rhythm completely unlike our daily cycle. One striking possibility is the existence of standing storm systems above the substellar point. Without rotation-induced day-night changes, clouds could build in massive spirals, drawing energy from the constant heat below. Lightning might strike endlessly in isolated areas, while strong winds drive moisture toward the twilight zone. There, precipitation could fall gently, rivers could flow steadily, and seas might remain liquid despite the frozen night side. The entire planet becomes a system of extremes: baking heat, frozen darkness, and a narrow band of temperate calm, a zone that could sustain life in ways Earth has never seen. Atmospheric composition plays a critical role. Even a thin layer of greenhouse gases can trap heat, extending the habitable zone along the terminator. Too little atmosphere and night-side ice dominates. Too thick, and the substellar point becomes scorching. NASA models suggest that with moderate carbon dioxide levels, winds along the twilight belt could stabilize surface temperatures between 0 and 30 degrees Celsius, perfect for liquid water. Cloud patterns could evolve dynamically, moving slowly along the ring, reflecting infrared radiation and contributing to heat balance. The climate in this scenario is a delicate dance, constantly balancing the extremes imposed by tidal locking and the steady star. The air of a planet shapes everything: weather, temperature, even the possibility of life. On TOI-700d, the atmosphere is the key to understanding what this alien world might really be like. We can't visit yet, but scientists are already imagining its skies, winds, and clouds in astonishing detail. They picture three main possibilities, each painting a completely different story. The first is the most hopeful: an Earth-like atmosphere. Imagine a planet with nitrogen making up most of its air, oxygen enough to breathe if you were there, and carbon dioxide just enough to trap heat without frying the surface. In this scenario, the planet's terminator, the twilight band between endless day and endless night, could be mild, temperate, and surprisingly familiar. Winds would carry warmth from the day side to the night side. Clouds could form in long streaks along the boundary, and rivers or shallow seas might persist, fed by gentle precipitation. The sky might glow reddish near the substellar point, fading to darker tones along the ring of twilight, where temperatures hover in a range comfortable for life. An Earth-like atmosphere would allow liquid water to exist where it matters most. The day side, constantly bathed in TOI-700's crimson light, could support shallow pools or seas, slowly evaporating into the air. Winds would move that moisture toward the twilight zone, condensing into clouds, forming rain, and returning to the surface in a cycle almost like Earth's, though stretched along a permanent horizon. Life, if it exists, would likely concentrate here. Plants, or plant-like organisms, could thrive in the dim red sunlight, capturing infrared energy to survive. Microbes might flourish in shallow pools, lakes, or damp soil along the terminator. Even the night side might hold pockets of liquid water beneath ice layers, warmed by residual heat transported from the day side. But what if TOI-700d doesn't have a gentle, Earth-like atmosphere? Imagine instead a Venus-like world wrapped in a thick layer of carbon dioxide. Here, greenhouse effects run unchecked. Heat from the substellar point could build relentlessly, trapped by a dense, heavy atmosphere that circulates sluggishly toward the dark side. The day side would become scorching, clouds dense with sulfuric acid, the sky thick and oppressive. Winds might be slow but powerful, carrying superheated air along the terminator. In this scenario, the twilight zone would shrink, its temperate belt squeezed by extreme heat from the day side and cold from the night side. Water would boil away, leaving dry rock and clouds of acid. Any hope for life would be almost entirely lost, at least as we know it. Then there's the Mars-like scenario, a thin, cold atmosphere dominated by carbon dioxide, but lacking the density needed to trap heat. Here, the night side becomes a frozen desert, the day side only mildly warmer. Winds would howl across a brittle surface, clouds rare, and precipitation almost non-existent. Water would exist only in small pockets, frozen for long stretches, or evaporating quickly in the brief warmth of the substellar point. In this world, the twilight zone might still offer slightly more hospitable conditions than the extremes, but life would be challenged to survive in such a tenuous atmosphere. Each scenario carries different consequences for potential biosignatures, the chemical fingerprints of life. In an Earth-like atmosphere, ozone could form in the upper layers, shielding the surface from harmful ultraviolet light. Methane, produced by microbial life or larger organisms, could mix with oxygen in a delicate balance, hinting at active biological processes. The combination of oxygen, methane, and ozone is particularly compelling to astronomers searching for life. They indicate that chemistry on the planet isn't just random, but shaped by living organisms. On a Venus-like planet, biosignatures would be far harder to detect. Thick clouds obscure the surface, and the hostile temperatures break down most molecules that could indicate life. Even if microbes survived in isolated pockets, their chemical signatures would be overwhelmed by the dense CO2 and sulfur compounds in the atmosphere. Observers from Earth would see a glowing red planet with little more than acid clouds and a crushing greenhouse effect. A Mars-like atmosphere offers a different challenge. Thin air allows radiation to reach the surface, which could break down potential biosignatures. Methane released by hypothetical microbes might disperse quickly. Ozone would be minimal, and oxygen levels too low to sustain complex life. Detection would require highly sensitive instruments capable of seeing tiny chemical traces across vast distances. This is where telescopes like the James Webb Space Telescope, JWST, come in. By analyzing the starlight filtered through TOI-700d's atmosphere, JWST can identify the chemical composition of gases millions of kilometers away. Every molecule leaves a subtle fingerprint in the light. Oxygen absorbs certain wavelengths, methane another, and ozone yet another. By looking for patterns, astronomers can infer whether the planet has an Earth-like balance or a runaway greenhouse. JWST could even distinguish between clouds, aerosols, and gases. For example, if the planet has thick CO2 clouds, the telescope might detect their scattering effects, while infrared observations could reveal the heat trapped in the atmosphere. Methane or oxygen in combination could hint at life. Even without directly imaging the surface, scientists can piece together a picture of the atmosphere's density, composition, and potential for supporting water. Every data point helps refine models, telling a story about how heat moves from the substellar point to the twilight zone, and whether liquid water could survive there. Visualizing these scenarios is thrilling. In an Earth-like world, clouds drift in long bands along the terminator, precipitation cycles maintain lakes and rivers, and winds carry warmth and moisture from day to night. The red light of the substellar point illuminates rocky landscapes, glinting off calm pools, while the night side remains cold but not barren, holding frozen reservoirs that feed back into the system. Life, if present, would thrive along this glowing twilight ribbon, adapted to a world of extremes, tempered by atmospheric circulation. A Venus-like TOI-700d tells a more dramatic story. Endless red heat presses down from the star, and the planet's surface shimmers with the greenhouse effect. Clouds form thick, acidic layers, casting deep shadows on jagged terrain. The twilight zone is narrowed by the oppressive heat, and winds howl sluggishly under the dense sky. Liquid water is gone, leaving the planet dry, alien and hostile, a warning of what happens when greenhouse gases spiral out of control. The Mars-like version is quieter, but just as stark. Ice dominates the night side, while the day side offers brief warmth. Winds whip across rocky plains, carving small canyons and moving sand. Clouds are thin and rare, rain almost non-existent, and the twilight zone a faint strip where temperatures allow for occasional melting. Life would have to be hardy, microbial, and hidden beneath the surface, waiting for fleeting moments when conditions allow. Each atmospheric scenario also affects heat distribution. A dense atmosphere, like Earth's or Venus's, can carry warmth efficiently from the substellar point to the night side. Thin atmospheres cannot, leading to extreme temperature contrasts. Winds are stronger when heat gradients are steep, and circulation patterns depend on the thickness, composition, and dynamics of the air. Clouds reflect sunlight, trap infrared radiation, and move along with the wind, affecting local climate in ways unique to tidally locked worlds. The possibility of biosignatures adds another layer of excitement. Detecting oxygen and methane together could indicate active biology. Ozone protects surface organisms from ultraviolet radiation. Even subtle chemical imbalances could hint at life adjusting the atmosphere over millennia. JWST and future telescopes will look for these signs, scanning the infrared spectrum and capturing the faint glow of gases millions of light-years away. For astronomers, every observation is like reading a message written in the chemistry of a distant sky. The terminator remains the star of the story. Across all three scenarios, it is the region most likely to maintain moderate temperatures. In Earth-like atmospheres, it could host rivers, lakes, and even primitive ecosystems. In Venus-like atmospheres, it might be a narrow, harsh belt separating extremes. In Mars-like scenarios, it could be a strip of occasional warmth, where ice melts temporarily, water cycles slowly, and conditions are just enough for microbial life to survive. These possibilities are not just speculation, they are grounded in real physics. The size of TOI-700d, its gravity, distance from the star, and the calm nature of TOI-700 itself all interact to create a system where atmospheres could exist for billions of years. A dense atmosphere traps heat and smooths extremes. A thin one exaggerates contrasts, and the composition determines the potential for water and life. When TOI-700d was first revealed to the public, the reaction was immediate and global. News outlets from CNN to the BBC splashed headlines about the discovery. NASA's TESS discovers its first Earth-sized planet in the habitable zone. National Geographic produced illustrations showing the red dwarf TOI-700 with its 3 orbiting planets, highlighting D as the one that could, in theory, have liquid water. For millions of people, the announcement was thrilling. Here was a planet, not light-years away in an abstract sense, but close enough to make the mind race with possibilities. A world orbiting a calm red dwarf, Earth-sized and in the star's temperate zone. Comparisons started circulating quickly. TOI-700d versus Kepler 186f, the first Earth-size exoplanet discovered in 2014's habitable zone, versus Proxima b, the closest exoplanet to the solar system, versus the multiple planets orbiting the TRAPPIST-1 system. Each comparison highlighted a different angle. Kepler 186f had the novelty of size and distance, Proxima b had proximity, and TRAPPIST-1 had the spectacle of 7 Earth-sized planets orbiting a red dwarf. TOI-700d, however, was unique. It was Earth-sized, in the habitable zone, and around a remarkably calm red dwarf. Emily Gilbert, a planetary scientist at NASA's Jet Propulsion Laboratory, was one of the leads on communicating the discovery. She emphasized that TOI-700d was potentially habitable, not confirmed to have life. The press release highlighted that while the planet is Earth-sized and in the temperate zone of its star, we do not yet know if it has an atmosphere, water, or conditions suitable for life. This distinction mattered. Headlines might scream Earth 2.0, but Gilbert and her colleagues reminded the public that habitability is a spectrum, and many factors, from atmosphere composition to radiation exposure, determine whether a planet could actually support life. Joseph Rodriguez, another key scientist from the Harvard-Smithsonian Center for Astrophysics, echoed this caution in interviews that potentially habitable doesn't mean inhabited. We have no evidence of life there yet. What we do have is an opportunity to study a planet that could, under the right circumstances, support liquid water. Expanding the family, the discovery of TOI-700e. In 2023, after years of continued monitoring of the TOI-700 system, astronomers confirmed the existence of a fourth planet, TOI-700e. This addition to the system marked a significant development in exoplanet science. TOI-700e is smaller than its sibling, TOI-700d, and orbits closer to the host star, placing it near the inner edge of the habitable zone. This configuration makes the TOI-700 system exceptional, as multi-planet systems with more than one planet in or near the habitable zone are extremely rare. TOI-700e was identified using the transit method. Observations from TESS had initially indicated subtle periodic dips in starlight that did not correspond to the previously known planets. These dips were faint, close to the detection threshold, and required repeated observation to confirm their planetary nature. Analysis of the light curves revealed a consistent 28-day orbital period, indicating a planet smaller than TOI-700d, with an estimated radius slightly under Earth's. The proximity of TOI-700e to the host star affects its energy balance. Receiving more stellar flux than TOI-700d, TOI-700e is expected to have higher surface temperatures. Simulations suggest that the incident flux places it at the inner edge of the star's habitable zone. While this increases the risk of a runaway greenhouse effect if the atmosphere is thick, it also makes TOI-700e a critical test case for understanding how planets near the inner habitable zone edge manage heat distribution. Tidal locking is likely for TOI-700e as it is for TOI-700d. Its short orbital period, combined with its proximity to the red dwarf, would result in synchronous rotation, meaning the same side constantly faces the star. This has profound implications for climate and habitability. Atmospheric models indicate that tidal locking leads to extreme day-night temperature contrasts, but efficient heat transport through winds and atmospheric circulation could moderate these extremes, particularly along the terminator zone. Mass estimates for TOI-700e remain constrained by modeling. Given its size, the planet is likely rocky, with a mass approximated at 0.91.1 times Earth's mass. Its gravitational environment is influenced by both the host star and neighboring planets, but dynamical simulations show that its orbit is stable over billions of years. The presence of TOI-700d further out does not significantly perturb the orbit of TOI-700e, suggesting a long-term stable configuration for both potentially habitable planets. TOI-700e's location in the system allows for interesting comparative planetology with TOI-700d. Both planets receive moderate stellar flux, yet the difference in orbital distance and stellar irradiation allows scientists to model how small changes in energy input affect climate stability, potential atmospheric retention, and liquid water distribution. This comparative study is particularly valuable because the host star, TOI-700, is unusually calm for a red dwarf. Its low flare activity reduces the likelihood of atmosphere stripping, increasing the probability that both planets could maintain atmospheres over long timescales. Spectroscopic follow-up observations are planned to characterize TOI-700E's atmosphere. The James Webb Space Telescope, JWST, offers the ability to detect atmospheric gases, including potential biosignatures. Depending on the thickness and composition of the atmosphere, JWST could identify gases such as oxygen, methane, or carbon dioxide. Differences in spectral signatures between TOI-700D and E would provide unprecedented insights into atmospheric evolution in multi-planet systems around red dwarfs. TOI-700E's discovery also informs models of planetary formation. Its small size and position suggest in situ formation near the inner habitable zone or moderate inward migration. Models of planetary accretion around low-mass red dwarfs indicate that rocky planets tend to form efficiently close to the star, while larger, gaseous planets form farther out. TOI-700E, therefore, provides a real-world example of these processes and allows for testing of formation models under conditions of low stellar mass and low stellar activity. The orbital architecture of the TOI-700 system is notable. TOI-700b orbits closest to the star, a hot, rocky world with a 10-day period. TOI-700c is larger, likely gaseous or icy, orbiting in between B and E. TOI-700E and D occupy the temperate zone, creating a configuration with two Earth-sized planets in potentially habitable conditions. Dynamical simulations show the system remains stable over gigayear timescales, and the planet's interactions do not induce strong eccentricities. This stability is unusual for red dwarf planetary systems, which often experience strong gravitational perturbations that can destabilize orbits or drive planets into the star. Climate simulations for TOI-700E indicate the potential for liquid water in the terminator region, provided an atmosphere exists. Heat redistribution models show that winds could transport energy from the day side to the night side, maintaining regions of moderate temperature. Depending on atmospheric thickness and composition, water could persist in stable regions along the substellar point and twilight zone. Comparing these conditions with TOI-700D allows scientists to examine how small differences in stellar flux and orbital distance affect habitability metrics. The discovery of TOI-700E also enhances the system's value for studying tidal effects. With two planets in similar orbits, the gravitational influence of one on the other may lead to subtle tidal heating, potentially affecting geology and internal heat. Tidal models suggest that while the effects are modest compared to tidal heating in closer-in exoplanets, they may still contribute to maintaining active geology or even influencing atmospheric dynamics. Understanding these processes helps refine habitability models for planets around red dwarfs. TOI-700E's detection demonstrates the increasing precision of exoplanet surveys. Its transit signal was weak, close to the noise level of TESS observations, and required extensive validation to confirm. This highlights how exoplanet detection has evolved. Small Earth-sized planets around faint stars, previously difficult to detect, are now observable with dedicated follow-up and advanced data processing techniques. The discovery reinforces the potential for more hidden planets in known systems, waiting for careful analysis to reveal them. Mass-radius relationships derived from models suggest that TOI-700E is likely rock-dominated, with a density comparable to Earth. If an atmosphere exists, it could support heat circulation and pressure levels conducive to liquid water. However, if the planet lacks a substantial atmosphere, surface temperatures on the day side could reach extremes, while the night side freezes, limiting habitable regions. Future atmospheric characterization will determine which scenario is more accurate. The discovery of TOI-700e also informs broader exoplanet statistics. Multi-planet systems with multiple potentially habitable planets are exceptionally rare. Prior to TOI-700e, only a handful of systems, such as TRAPPIST-1, had multiple temperate worlds, and most orbit active stars prone to flares. TOI-700 now joins a very short list of quiet red dwarf systems where multiple temperate planets can exist over long periods. This has implications for estimating the frequency of potentially habitable planets in the galaxy. Dynamical stability studies indicate that TOI-700e's orbit is not resonant with TOI-700d, but the planet's periods are close enough to allow minor gravitational interactions. These interactions are insufficient to destabilize the system, but may contribute to orbital circularization over long timescales, minimizing eccentricity-induced climate variations. The system thus represents a stable laboratory for understanding multi-planet habitability dynamics. The proximity of TOI-700e to TOI-700d also allows for comparative atmospheric studies. If both planets have atmospheres, JWST and other observatories could detect differences in composition, cloud coverage, and thermal profiles. These comparisons would provide the first direct test of how stellar flux and orbital distance affect atmospheric evolution in a multi-planet system around a red dwarf. The insights gained could refine models for thousands of other red dwarf planets discovered by TESS and Kepler. TOI-700e's discovery shows the importance of long-term monitoring. The planet's faint transit signal illustrates that even relatively nearby systems may harbor hidden planets with subtle signatures. Continued observation, improved algorithms, and dedicated follow-up are essential to uncover these worlds, refine their orbital parameters, and characterize their potential habitability. TOI-700e is a clear example of how patient, systematic observation can reveal previously hidden planets that fundamentally alter our understanding of nearby planetary systems. With TOI-700e, the system now contains 4 planets, 2 of which occupy the temperate zone. This arrangement provides an unparalleled opportunity to study planetary formation, orbital stability, tidal effects, and habitability within a single nearby system. TOI-700e is smaller and receives more stellar flux than D, allowing scientists to explore how slight differences in energy input influence potential atmospheres and surface conditions. The discovery represents a critical step in exoplanet science, demonstrating that even quiet red dwarfs can host multiple temperate planets and offering a laboratory for testing the limits of planetary habitability. TOI-700e orbits significantly closer to the star than TOI-700d. Its semi-major axis is roughly 0.13 AU, compared to 0.163 AU for D. This places E near the inner edge of the star's habitable zone, whereas D sits closer to the middle. The closer orbit translates into a shorter orbital period. TOI-700e completes one orbit every 28 days, while TOI-700d takes 37.4 days. That difference of 9 days might seem minor, but it has consequences for planetary climate, stellar energy input, and tidal interactions with the host star. Because TOI-700e receives more energy from the star, surface temperatures, assuming an Earth-like atmosphere, are expected to be higher than on D. Climate models suggest that E's substellar point, the region permanently facing the star due to tidal locking, could experience more intense heating, while the night side remains frigid. The terminator, the twilight zone between day and night, may host temperatures suitable for liquid water, but the region could be narrower than on DD due to the stronger gradient between the day and night sides. This contrast allows scientists to explore how small changes in stellar flux affect the habitability of tidally locked planets. While both planets are Earth-sized and rocky, the difference in orbital distance provides a natural experiment. The comparison helps refine models of heat redistribution, atmospheric circulation, and surface temperature patterns under tidal locking. It also illustrates how subtle differences in orbital properties can have major effects on potential climates. Orbital architecture is another key distinction. TOI-700 E and D are separated by a relatively small gap in semi-major axes, yet both maintain stable, nearly circular orbits. Dynamical simulations indicate that the system is remarkably stable, with minimal gravitational interactions between the two planets. Unlike many red dwarf systems, where planets in close orbits often destabilize each other over millions of years, TOI-700 E and D appear locked in a long-term stable configuration. This stability provides clues about the system's formation history and the processes that allowed multiple temperate planets to survive in a single red dwarf system. The difference in orbital distance also affects surface illumination patterns. Both planets are likely tidally locked, but the intensity of illumination at the substellar point differs. On E, the higher stellar flux may lead to stronger atmospheric convection, faster winds, and potentially more active cloud formation. On D, the lower flux suggests a gentler energy gradient, possibly allowing for a wider, more temperate terminator region. Studying these differences can reveal how stellar flux shapes atmospheric dynamics on rocky, tidally locked planets. The proximity of E to the star also has implications for tidal heating and planetary geology. Tidal locking generates internal friction, which can produce heat in a planet's interior. Because E orbits closer, tidal forces are slightly stronger than on D. While not extreme, this additional energy could influence geological activity, possibly sustaining volcanism or driving tectonic processes that recycle surface materials and gases. By contrast, D receives slightly weaker tidal forces, meaning its geological activity may be more subdued. Comparing the two planets allows scientists to examine how tidal effects vary with orbital distance and impact planetary evolution. From a system-wide perspective, the presence of two temperate planets challenges existing theories of planet formation around small stars. Red dwarfs like TOI-700 are low-mass stars with relatively faint protoplanetary disks. Conventional models suggest that forming multiple Earth-sized planets in the habitable zone of such stars is difficult due to limited material and potential migration during early system evolution. TOI-700, however, demonstrates that two rocky, temperate planets can coexist, implying either unusually efficient planet formation, minimal orbital migration, or a combination of both. This discovery forces theorists to revisit assumptions about disk mass, accretion rates, and migration dynamics in red dwarf systems. The arrangement of B, C, E, and D provides a test case for planetary spacing and orbital resonances. TOI-700 and D are not in a simple resonance, but the spacing appears finely tuned. Simulations suggest that if E were slightly closer or D slightly farther, gravitational perturbations could destabilize the system over gigayears. The current architecture indicates a delicate balance established either during formation or through long-term orbital evolution. Understanding how these planets settled into their current orbits may shed light on why multi-habitable planet systems are so rare. Atmospheric retention is another area where differences between E and D matter. Being closer to the star, E is exposed to stronger stellar radiation, which can erode atmospheres over time. However, TOI-700 is unusually calm for a red dwarf with low flare activity. This reduces atmospheric stripping, increasing the likelihood that both E and D could maintain substantial atmospheres. Still, small differences in incident flux mean that E's atmosphere may require slightly higher surface pressure or more efficient heat redistribution to remain stable, whereas D enjoys a wider margin for habitability. The contrast between E and D also informs future observation strategies. JWST and other telescopes will be able to compare the two planets' atmospheres directly. Differences in spectral features, such as water vapor, carbon dioxide, and methane, could reveal how slight variations in stellar flux influence atmospheric composition. The presence or absence of clouds, differences in thermal emission, and potential biosignatures can all be studied comparatively. This is unprecedented. Rarely do astronomers get two Earth-sized planets around the same star, each offering slightly different conditions for habitability. The two planets also provide insight into climate modeling under tidal locking. On E, models suggest the day side could be hotter and the night side colder than on D, due to stronger stellar irradiation. Winds might circulate more vigorously, transporting heat toward the night side, but the terminator could be narrower. On D, the smaller energy gradient may produce a more stable, temperate region along the twilight band. Comparing circulation patterns, cloud formation, and potential water stability between E and D allows scientists to test assumptions about climate dynamics on tidally locked planets in a real-world setting. The discovery also has implications for multi-habitable zone planetary systems. Prior to TOI-700e, the majority of red dwarf systems with potentially habitable planets contained only one. TOI-700 demonstrates that it is possible for two planets to occupy similar habitable zones, maintain stable orbits, and resist atmospheric erosion. This challenges models predicting that red dwarf activity or orbital instability should limit the number of temperate planets. It suggests that some quiet red dwarfs may host more complex multi-habitable zone systems than previously thought. Orbital comparisons also reveal potential for subtle planet-planet interactions. While the system is dynamically stable, the proximity of E to D may induce small tidal or gravitational perturbations. These interactions could influence orbital eccentricity, which in turn affects seasonal variations and heat transport. The comparison between the two planets allows modelers to estimate the range of possible climates and the role of orbital mechanics in shaping habitability. The differences in stellar irradiation also help scientists refine models of planetary atmospheres under variable energy input. TOI-700e, receiving more flux, may have stronger photochemical reactions in its atmosphere, affecting ozone, methane, and carbon dioxide cycles. TOI-700d with lower irradiation may sustain different chemical balances. The journey to TOI-700d. When you hear that TOI-700d and E are just over 100 light-years away, it sounds close in cosmic terms. 100 light-years. Easy to say, but try to picture what that really means. 1 light-year is the distance light travels in a single year, roughly 9.46 trillion kilometers. Multiply that by 100, and you get 946 trillion kilometers. That's a number almost impossible to imagine. Even at the speed of light, which nothing with mass can reach according to current physics, it would take 100 years to get there. Now let's slow it down to reality. What about our fastest spacecraft? Voyager 1, launched in 1977, is currently leaving the solar system at about 17 kilometers per second. That's 61,000 kilometers per hour. Fast by human standards, but in cosmic terms, it's glacial. At that speed, Voyager 1 would take over 16 million years to reach TOI-700. New Horizons, which zipped past Pluto in 2015 at roughly 16 kilometers per second, wouldn't be much faster. The Parker Solar Probe, currently the fastest human-made object relative to the Sun, travels at nearly 700,000 kilometers per hour at its closest approach to the Sun. Impressive, yes, but it would still take more than 17,000 years to make the journey. We're left with the cold truth. With current technology, TOI-700d and E are unreachable, but that doesn't stop the imagination or the science. These planets have sparked serious thinking about what interstellar travel could look like if humans were determined to reach even the closest potentially habitable planets. Enter conceptual interstellar missions. One of the most well-known is Breakthrough Starshot, a project aiming to send tiny, lightweight probes to nearby stars using laser sails. The idea is simple in theory, but mind-blowing in scale. A spacecraft no bigger than a postage stamp is attached to a reflective sail. A massive laser array on Earth accelerates the sail to a fraction of the speed of light, up to 20% the speed of light, according to current proposals. At that speed, a probe could reach a system like TOI-700 in roughly 500 years. That's still centuries, but compared to millions of years, it's almost instantaneous. Laser sails have unique advantages. A spacecraft that's small doesn't need fuel, only the push of light. It can carry cameras, sensors, and communication devices to send back data about distant planets. Imagine a probe zooming past TOI-700 D and E, measuring atmosphere composition, temperature, or even surface conditions along the terminator line where day meets night. The data would arrive decades or centuries later, but it would provide a first close-up look at a potentially habitable exoplanet. Beyond light sails, scientists have imagined fusion-based propulsion. Fusion drives, if ever perfected, could generate continuous acceleration by fusing atoms to release energy. These drives could reach significant fractions of light speed, cutting travel time from hundreds of thousands or millions of years to several centuries or less. Fusion drives could potentially carry larger payloads than tiny laser probes, meaning more instruments, more redundancy, and maybe even life support for robotic missions. For interstellar travel enthusiasts, fusion drives are a tantalizing possibility, though building one capable of sustained operation in space remains decades away from feasibility. There are even wilder concepts, more in the realm of theoretical physics, warp drives or space-time manipulation. Here, a spacecraft wouldn't move faster than light in the traditional sense, but would instead compress space ahead and expand space behind, effectively shortening the distance. According to general relativity, this is theoretically possible, though it requires forms of matter or energy we haven't discovered or even created. If someone cracked it, a journey to TOI-700 could take years instead of centuries. These ideas remain speculative, but fuel thinking about what the far future of exploration might look like. Even if humans could send probes, the challenges of interstellar space are immense. The interstellar medium, the thin gas and dust between stars, poses risks at high velocities. A particle traveling at 20% the speed of light could hit interstellar dust with enough force to damage or destroy a probe. Shields or protective designs are critical, but again the engineering challenges are immense. Communication is another obstacle. A signal traveling back to Earth from TOI-700 would take 101 years at light speed. Real-time control is impossible. Probes would need autonomous decision-making and artificial intelligence sophisticated enough to adapt to unexpected situations. Despite the obstacles, imagining a mission to TOI-700 isn't purely academic. Studying these planets from afar helps refine mission concepts. Knowing the star is calm, with low flare activity, makes designing probes easier because high-energy radiation isn't constantly bombarding instruments. The presence of two potentially habitable planets also influences mission planning. Would you send a probe to the inner planet first, then the outer? Could a single probe sample both, or would you need multiple missions? Questions like these make TOI-700 a testing ground for interstellar mission design. The orbital differences between D and E also matter. TOI-700E's closer orbit means it experiences more stellar energy, potentially affecting its atmosphere. A probe could measure these differences directly, providing a rare dataset on how small variations in distance from a red dwarf affect climate, atmospheric chemistry, and potential habitability. Meanwhile, TOI-700D's cooler, more temperate orbit allows comparison under slightly less intense irradiation. For scientists, these two worlds are natural laboratories that could test climate and habitability models in ways impossible within our solar system. Another consideration is energy for return missions. Sending a probe to TOI-700 is one thing. Returning samples is another. Current concepts focus on one-way missions because deceleration at 20% light speed requires massive energy, likely more than the probe can carry or generate. In theory, a laser deceleration system or gravitational braking using the target star could slow a probe, but these are hypothetical at best. Even so, the possibility of sending instruments that orbit the planets and relay data over decades is already revolutionary. Thinking about human travel makes these numbers feel even more staggering. If a generation ship traveled at 1% of light speed, 30,000 kilometers per second, it would still take 10,000 years to reach TOI-700. Maintaining life support, food, radiation shielding, and social stability over millennia pushes human imagination to the edge. Concepts like suspended animation or cryogenic sleep have been proposed, but these remain science fiction. For now, humans visiting these planets is far beyond reach. Probes are the real frontier. Even small advances in propulsion could shrink the timescale. If a probe could reach 10% of light speed, the journey becomes about 1,000 years, which, while still daunting, makes interstellar study conceptually plausible for long-term projects. The engineering challenge is immense, but TOI-700 offers motivation. A system with a quiet star, 2 temperate planets, and Earth-like sizes provides one of the most promising nearby targets for studying potentially habitable worlds. Beyond propulsion, communication methods are being considered. A probe at TOI-700 would need to send data over 101 light-years. Laser communication systems offer narrow, high-bandwidth beams that could transmit images, spectra, and environmental readings. Even so, it would take a century for the first signals to reach Earth. Scientists are modeling how probes could store and prioritize data, ensuring the most critical information arrives first. On planets like D and E, with temperature extremes, low light, and potentially thin atmospheres, every system must be resilient and highly reliable. Failures could go unnoticed for decades. Next, consider tidal locking, a condition likely affecting both D and E. Tidal locking means the same side of the planet always faces the star. There is no sunrise or sunset in the traditional sense. One hemisphere is in eternal daylight, constantly bathed in the star's glow. The other hemisphere is in permanent night. Between these extremes lies the terminator line, a narrow twilight zone where temperatures are more moderate. This has dramatic consequences for anyone or anything trying to operate on the surface. On the day side, temperatures could be significantly higher than on Earth, particularly on TOI-700e, which receives more stellar energy. Models suggest that if the planet has an atmosphere similar to Earth, heat would be redistributed by winds, but extremes would still exist. Hot, sun-facing regions could experience temperatures approaching or exceeding 40–50 degrees Celsius. Without an atmosphere, the difference becomes brutal. The substellar point could roast under constant light, while the night side freezes at temperatures well below 100 degrees C. Any probe would need thermal control systems capable of handling extreme gradients. The night side presents a different challenge. With no sunlight, the temperature plummets. On D, which receives slightly less energy, the night side could stabilize around 50 to 70 degrees C with a thin atmosphere. On E, closer to the star, night side temperatures might drop even lower if heat redistribution is inefficient. For human explorers, this means permanent night regions are effectively frozen wastelands. For probes, electronics would need insulation and possibly active heating to avoid system failure. Another critical factor is radiation. While TOI-700 is quiet, the planets are still subject to cosmic rays and residual stellar radiation. The lower magnetic field of a small red dwarf means charged particles from the interstellar medium can more easily penetrate planetary atmospheres. For humans, this would require substantial shielding, but for probes, it affects instrument longevity and reliability. Instruments designed for Earth orbit may fail more quickly under these conditions, so hardened electronics are essential. Atmospheric composition further shapes the environment. If TOI-700D or E has an Earth-like atmosphere, it would offer some protection against radiation and help moderate surface temperatures. Thick atmospheres could distribute heat more evenly, reducing extremes between day and night sides. Thin atmospheres, or atmospheres dominated by carbon dioxide, could make surface conditions far more hostile. For example, a Venus-like atmosphere could trap heat on the day side, causing temperatures above 100 degrees Celsius, while a Mars-like thin atmosphere could fail to retain any heat, plunging nightside regions to extreme cold. Probes would need to be designed with these possibilities in mind, including pressure-resistant housings or cooling systems. Low light is another challenge. Red dwarfs emit mostly infrared light, with very little visible spectrum compared to the Sun. Even on the day side, the planet would appear dimmer than Earth under daylight. Cameras, spectrometers, and other instruments would need enhanced sensitivity. For humans, vision would be limited. Skies may appear reddish-orange, and the intensity of daylight would feel weaker than on Earth. Energy generation from solar panels would be less efficient, requiring alternative power solutions such as nuclear batteries or highly sensitive photovoltaics. Surface conditions are also affected by planetary gravity. TOI-700 days and E are close in size to Earth, slightly larger in radius, and possibly slightly higher in mass. Gravity is therefore similar, though marginally stronger. This is favorable for probe landing, as instruments would not face extreme differences in weight. For humans, mobility would be comparable to Earth, assuming an atmosphere thick enough to allow for conventional walking or machinery operation. If the atmosphere is thin, pressure suits or pressurized habitats would be required. Wind and weather patterns are unpredictable. On tidally locked planets, winds flow from the hot day side to the cold night side, potentially reaching hundreds of kilometers per hour. Atmospheric simulations suggest that on E, which receives more energy, winds could be stronger than on D, particularly near the terminator. These high-velocity winds could influence probe stability and even erode unprotected materials. Dust storms or localized weather systems could form in areas of extreme temperature contrast, requiring careful engineering for surface operations. Water availability is another concern. If liquid water exists, it is most likely confined to the terminator zone. Dayside regions may be too hot, nightside regions too cold. For probes, targeting this narrow, habitable belt is essential for detecting oceans, ice, or any signs of chemical activity. Human missions, if ever possible, would have to locate or artificially create livable zones, either in the twilight band or in domed habitats with controlled temperatures. Even sunlight on the day side behaves differently than on Earth. The red dwarf spectrum is dominated by longer wavelengths, meaning photosynthesis, if any exists, would operate differently than on Earth. Plants, if hypothetically present, would need pigments tuned to red and infrared light. For human explorers or probes equipped with cameras, familiar visual cues like blue skies or green vegetation might be absent, making navigation and observation more challenging. Dust and micrometeoroid impacts are additional hazards. Even in calm stellar environments, interplanetary dust can cause damage at high velocities. Probes traveling at or near orbital speeds around the star or descending to the surface would need shields or redundant systems to survive. Human missions would face the same threats, compounded by the necessity of life support and radiation protection. And there's the psychological and operational aspect for humans. Constant daylight or constant night can disrupt circadian rhythms, affecting sleep, cognition, and physical health. Extreme temperature gradients would require careful planning for habitat placement and movement. Food production would rely on artificial light and carefully controlled environments. Even with ideal conditions, life on TOI-700D or E would be profoundly different from life on Earth. Probes would face extreme temperature differences between day and night sides, low light levels, variable winds, and potential radiation exposure. Human explorers would need pressurized habitats, thermal regulation, and radiation shielding, even in the most favorable regions. The terminator zones offer the most reasonable environment, with moderate temperatures and potential liquid water. But the challenges of energy generation, communication delay, and planetary weather are immense. Mission design also benefits from what we know about TOI-700's stellar environment. The star's low activity means less risk from high-energy flares, which would otherwise threaten electronics and instruments. Unlike Proxima Centauri or other active red dwarfs, TOI-700 is quiet and stable, making navigation, instrumentation, and long-term probe survival more feasible. Knowing this allows engineers to optimize shielding and power requirements, focusing resources on propulsion and data collection, instead of radiation mitigation. Even our nearest neighbors, like Proxima Centauri at 4.24 light-years, are far. 100 light-years is orders of magnitude beyond current human reach. While we may never physically reach TOI-700 D and E in our lifetimes, the system drives research, fuels interstellar mission concepts, and provides one of the best opportunities to test our understanding of habitable worlds beyond the solar system. Probes could tell us about atmospheres, temperatures, surface conditions, and maybe even hints of biosignatures, giving us the closest possible glimpse of these distant Earth-sized planets. Imagining a trip to TOI-700 also highlights the urgency of current telescopes. JWST, the extremely large telescope, and future observatories can study these planets from afar, measuring atmospheric gases and thermal properties. Every observation is a step closer to visiting these planets in a scientific sense, even if no human will set foot there for thousands, if not millions of years. The next frontier of exoplanet science. When astronomers first confirmed TOI-700 D in 2020, it became a reference point for what we might expect from future discoveries around red dwarfs. Before TOI-700, scientists largely relied on statistical models and indirect observations. Kepler gave us a catalogue of candidate planets, many of them tantalizing, but confirmation was tricky. Red dwarf planets in particular were often dismissed as too hostile due to the violent behavior of their parent stars. TOI-700 days flipped that narrative. Here was a planet with the right size, in the right orbit, around the right kind of star, conditions that suggested the possibility of an atmosphere, liquid water, and even the subtle chemistry that makes life plausible. And that makes TOI-700 D a template. The lessons it offers go beyond its immediate system. For one, it shows that even modest telescopes like TESS can detect small Earth-sized planets in temperate zones if the star is quiet enough. It teaches us what signals to look for: subtle dips in brightness, faint transits, carefully analyzed orbital periods. The precision needed is huge, but TOI-700 demonstrates that these signals are not only detectable, they're actionable. Scientists can now design surveys and follow-up observations targeting stars with similar properties, increasing the odds of finding other potentially habitable worlds. The planet also redefines what habitable actually means. In textbooks, habitable zones are often simplified, the range of distances where water could remain liquid on a planetary surface. But TOI-700 D illustrates that habitability is more complex. It's about stellar behavior, tidal locking, atmospheric retention, and even orbital stability. One planet in a habitable zone may be blasted by flares, another, like D, may thrive quietly for billions of years. The discovery forced scientists to rethink the balance of factors that make life possible beyond the solar system. It's no longer just distance from a star. It's the combination of orbital architecture, stellar temperament, and planet size. TOI-700 days also informs future missions. TESS, with its wide-field survey, is excellent for finding planets around bright nearby stars. Kepler, though no longer operating, taught scientists how to detect small planets over long timescales. Together, the two missions provided the foundation for identifying TOI-700 D. But the real game-changer comes with JWST and the next generation of telescopes. Using TOI-700 D as a reference, astronomers can focus on spectral features that indicate atmospheric composition: carbon dioxide, methane, water vapor, and oxygen. They can refine models of heat distribution on tidally locked worlds, anticipate cloud cover in terminator zones, and predict where stable regions for liquid water might exist. TOI-700 days is the real-world proof that these methods work. And it's not just about detection. TOI-700 days reshapes our scientific priorities. Previously, we might have focused on sun-like stars, assuming that Earth analogues would be easier to recognize around them. TOI-700 proves that red dwarfs, despite their small size and dim light, can host planets that deserve serious attention. It tells us that quiet red dwarfs should be a top priority in exoplanet surveys. Future missions will likely dedicate significant observation time to stars with similar profiles: stable, small, and nearby. The architecture of the TOI-700 system itself is instructive. With at least 4 planets, B, C, D, and E, it shows how multiple planets can coexist in stable orbits around a red dwarf, even when 2 of them occupy orbits in or near the habitable zone. This has implications for planet formation theories. Small stars were once thought to have limited material in their protoplanetary disks, restricting the number of large, rocky planets they could form. TOI-700 challenges that assumption. Its system demonstrates that multiple temperate planets can form, migrate minimally, and maintain long-term stability. That means our models must account for the possibility of complex planetary systems even around low-mass stars. TOI-700 days also offers a case study in tidal locking and climate modeling. Unlike Earth, where a 24-hour day distributes solar energy evenly, D's one hemisphere faces the star continuously, while the other remains in darkness. Simulations of its atmosphere show that winds could circulate heat from the day side to the night side, creating a band of temperate conditions along the terminator. Studying this helps scientists understand how life might survive in extreme settings, how atmospheric circulation behaves under constant irradiation, and what kinds of climate signatures future telescopes might detect. This is where JWST and other next-generation observatories come into play. TOI-700 days provides a testing ground for spectroscopy techniques aimed at detecting potential biosignatures. For instance, combinations of ozone, oxygen, and methane could suggest chemical disequilibrium caused by biological processes. Understanding what to look for and how stellar spectra affect detection is critical. TOI-700d, with its known properties, allows scientists to calibrate instruments, test models, and refine strategies for observing even more distant and challenging systems. Another lesson is the importance of stellar characterization. Early data misclassified TOI-700, making the planets seem larger and hotter than they really were. Correcting the star's size and temperature immediately transformed D into a habitable zone candidate. This shows how critical accurate stellar measurements are. Missions must not only find planets, but also precisely measure the stars they orbit. TOI-700 days is a clear example of how a single correction can completely reshape our understanding of a planet's potential for habitability. The system also emphasizes the value of multi-planet comparisons. With the discovery of TOI-700e, scientists can compare 2 temperate planets in the same system. How does a slightly closer orbit affect climate, atmospheric retention, or tidal heating? What does a marginally higher stellar flux do to potential biosignatures? These questions are easier to answer with 2 planets sharing a star, because the variables are controlled. Stellar age, metallicity, and activity level are constant. TOI-700 days provides the benchmark. E provides the contrast. Together, they offer a real laboratory for exoplanet science. From a broader perspective, TOI-700d informs our understanding of planetary habitability across the galaxy. The galaxy is dominated by red dwarfs, meaning that Earth-sized planets in temperate zones around these stars may be more common than previously thought. But many red dwarfs are violent. TOI-700 days tells us that quiet red dwarfs are particularly valuable. They are the best candidates for finding stable, habitable planets. It reframes our search, showing that it's not just about quantity of planets, but the quality of the host stars. TOI-700 days also pushes the frontier of exoplanet science because it is within reach of observation. At 101 light-years, it is far, but not impossibly so. JWST and future telescopes can probe its atmosphere, detect thermal emissions, and even test climate models developed from simulations. The system gives scientists a concrete target for advancing our understanding of habitability in ways that were speculative just a few years ago. It is the bridge between theory and observation, between modeling and real data. In many ways, TOI-700d is a Rosetta Stone for red dwarf planets. It shows us how to detect Earth-sized planets, how to evaluate their habitability realistically, how to design observations, and how to refine models of climate, tidal locking, and atmosphere. It shows that habitable planets are not only possible around small stars, but that they can exist in multiple planet systems with surprising stability. Every new red dwarf we study can be measured against D, making it the prototype for the next wave of exoplanet discoveries. The lessons extend even further. Understanding TOI-700d helps inform future interstellar mission concepts. Whether planning probes, laser sail missions, or even speculative human exploration, having a reference planet with known properties is invaluable. Knowing the star's stability, the planet's sizes, orbits, and potential climates reduces uncertainty and focuses research efforts. TOI-700 days transforms distant theory into actionable science. It also inspires new questions. Could a quiet red dwarf system host more than 2 habitable planets? How do minor variations in orbital distance affect atmospheric retention? Could tidal locking create unexpected microclimates, with liquid water confined to narrow bands or even isolated pockets? Each observation of D provides the data needed to explore these questions, and each answer shapes the strategy for observing hundreds of other red dwarf systems. For most exoplanets, even ones relatively close to us, direct imaging is a huge challenge. Stars are bright, planets are small and dark, and the distance is immense. TOI-700 days sits 101 light-years away. That's 946 trillion kilometers. From Earth, it's a faint flicker next to a glowing star, essentially invisible to conventional telescopes. That's where the next generation of observatories comes in. Habitable, Dwarf, and Life are designed to do what no previous telescope could: separate the faint light of a small planet from the overwhelming glare of its host star. The goal is direct imaging, literally seeing a planet as a tiny dot in the vastness of space, orbiting a star that glows hundreds of thousands of times brighter. Imagine it, a pale blue circle, faint but unmistakable, tracing its orbit around a quiet red star. That image alone would redefine exoplanet science. Habitable, the Habitable Exoplanet Observatory, is designed to look for Earth-sized worlds around nearby stars. Its strength lies in coronagraph technology, which blocks out the light of the star, allowing the faint reflection from the planet to shine through. With Habitable, scientists hope to capture the spectrum of planets like TOI-700d, detecting the chemical fingerprints of their atmospheres. This is where things get fascinating. We are no longer limited to orbital measurements or transit light curves. We can see the planet's atmosphere, detect water vapor, carbon dioxide, oxygen, and even more complex molecules that hint at the possibility of habitability. Dwarf, the large UV/optical/IR surveyor, takes this a step further. Larger, more powerful, and designed to cover a broader range of wavelengths, Dwarf could map surface features on nearby planets, detect seasonal changes, and measure cloud patterns in their atmospheres. For TOI-700d, this means we could test climate models that have been purely theoretical until now. We could see whether heat circulates effectively from the day side to the night side on a tidally locked world. We could detect where potential liquid water accumulates, perhaps in the twilight zones where conditions are most stable. Life, the large interferometer for exoplanets, is an entirely different approach. By using multiple telescopes in a coordinated array, Life can achieve extraordinary resolution, isolating planetary light with unprecedented precision. This would allow scientists not just to detect molecules, but to measure subtle variations in temperature, atmospheric composition, and even surface reflectivity. For TOI-700d, Life could provide data precise enough to distinguish between a thick CO2 atmosphere like Venus, a thin Mars-like atmosphere, or something closer to Earth's balance of nitrogen and oxygen. But there's a subtle point here that often gets lost in popular coverage. The question scientists actually ask is not, is there life? It's much more measured. Can this planet support life? That is the real, tangible goal. Direct imaging allows us to measure parameters that determine habitability, stellar flux, atmospheric composition, temperature distribution, and orbital stability. Life may or may not exist, but understanding whether it could exist is a critical first step. TOI-700 days is a case study in this approach. The physics of TOI-700d makes it ideal for these future observatories. Its host star is small, cool, and remarkably quiet. That reduces the background noise from stellar flares, making the planet's faint reflected light easier to isolate. Its radius, slightly larger than Earth, increases the total surface area, meaning slightly more reflected light than a smaller planet would produce. Its orbit, at 0.163 AU, is close enough to receive adequate stellar energy, but far enough to avoid being engulfed in the star's glare. From an observational standpoint, it's an optimal candidate. Imagine what direct imaging would reveal. The terminator zone, the narrow band between eternal day and eternal night, could be seen as a subtle gradient of brightness. A thick atmosphere would diffuse light across the day side, softening the contrast with the night side. Clouds, if present, would cast shadows and create patterns that indicate wind flow. Even seasonal variations might be detectable if the planet has any axial tilt. Every observation would feed directly into climate models, refining our understanding of how tidally locked planets distribute heat. Spectroscopy adds another layer. With Habex or LUVOIR, scientists could detect absorption features in the light reflected from TOI-700d. Water vapor would absorb at specific wavelengths, carbon dioxide at others. Oxygen and ozone have distinct signatures in the UV and visible ranges. Methane, often associated with biological processes on Earth, would appear in the infrared. By combining these data, scientists could infer whether the atmosphere is stable, whether greenhouse gases are present in balanced amounts, and whether surface conditions could support liquid water. These are not speculative measurements. They are concrete, measurable parameters that define habitability. The ability to compare TOI-700d with its sibling, TOI-700e, adds another dimension. Direct imaging of both planets would provide a rare opportunity to study two potentially habitable worlds in the same system. Differences in orbit, illumination, and atmosphere could reveal how small variations in stellar energy affect climate, heat distribution, and atmospheric retention. This comparative approach is critical. It allows scientists to move beyond single-planet studies, testing broader hypotheses about habitability around red dwarfs. But the challenges are huge. The planets are incredibly small relative to the star. The light they reflect is minuscule, 1 part in a billion compared to the host star. Any observation must account for instrumental noise, cosmic rays, and interference from the interstellar medium. Engineers must design coronagraphs and interferometers with extreme precision, and data processing techniques must filter out every possible source of error. Observing TOI-700d directly is not a simple task. It is a pinnacle of modern engineering and astronomy. Even distance complicates matters. At 101 light-years, the light we see left TOI-700d a century ago. Any observation is a snapshot of a planet in the past. That adds an intriguing challenge for scientists. They are effectively studying a moving target whose current conditions may be slightly different. Despite this, the fundamental physics of orbit, stellar radiation, and planetary reflection remain consistent, allowing meaningful models to be built. The stakes are high because the payoff is big. Imagine capturing an image of TOI-700d, analyzing its spectrum, and confirming that its atmosphere is stable and suitable for liquid water. That data would become the baseline for thousands of future exoplanet studies. Every red dwarf with a quiet star nearby would be measured against it. Future observatories would prioritize systems similar to TOI-700, applying lessons learned from its direct imaging. It's also a question of human imagination. Seeing a planet directly, an actual blue dot orbiting a red star, changes the conversation. It moves exoplanet science from the realm of graphs and simulations into a tangible reality. Even without confirming life, just being able to see such a world, measure its spectrum, and analyze its atmosphere is a profound leap. TOI. 700 days becomes more than a discovery. It becomes a benchmark for what is possible. Habitable, Louvois, and life are not just tools. They are the bridge between theoretical modeling and practical exploration. They will turn hypotheses into observable phenomena. TOI, 700 days will teach them how to separate planet light from stellar glare, how to identify atmospheric components, and how to interpret subtle climate signals. Every observation will refine models, inform future telescope design, and shape the next generation of interstellar targets. And it doesn't stop there. The techniques developed for TOI-700D could eventually be applied to planets even farther away or around more active stars. Each new observation improves instrumentation, refines data analysis, and increases confidence in habitability assessments. TOI. 700 days is the starting point for a systematic expansion of exoplanet science, where every planet can be measured, compared, and modeled in increasingly precise ways. The ultimate goal remains cautious but profound. Scientists do not yet ask if life exists. That question is centuries away, given the limitations of technology and distance. Instead, they ask, can this planet support life? Direct imaging is the method that answers that question. It allows us to observe the atmosphere, climate, and surface conditions directly, rather than inferring from transits alone. TOI. 700 days provides the first realistic opportunity to do this for an Earth-sized planet around a red dwarf. The implications extend beyond the planet itself. By validating direct imaging techniques and atmospheric characterization, TOI-700D informs the search for countless other worlds. It establishes protocols for identifying the best candidates, modeling potential climates, and prioritizing targets for observation. It turns abstract questions into concrete research agendas and sets the stage for the next decades of exoplanet discovery. Habitable, Louvois, and life will turn the distant flicker of a red star into a measurable, analyzable, and even visually discernible planet. And while the question of life remains unanswered, the question of habitability has never been closer to a real answer. The future of exoplanet science is here, and TOI-700D is leading the way. Every photon it reflects carries information about climate, atmosphere, and potential habitability. Every observation made by future telescopes will expand our understanding of what planets like it can be. The quiet red star, the tidally locked orbit, the temperate zone, it all converges into a real, tangible target for human curiosity and scientific rigor. TOI. 700 days has moved from being a point in a dataset to a measurable, understandable world. And in doing so, it defines the next frontier of exoplanet science. Climate, chemistry, and chance. When we talk about TOI-700D, we can measure its size, track its orbit, and even estimate its surface temperature. But that's just the surface of the story. The real intrigue lies in its climate, its chemistry, and the razor-thin margin that separates a world where water can persist from one where it evaporates or freezes. Habitability is never guaranteed. On a planet like this, it comes down to a delicate balance of forces: greenhouse gases, magnetic fields, rotation, and even the role of oceans. TOI. 700 days orbits its quiet red dwarf every 37 days. That seems fast compared to Earth's 365-day year, but in terms of energy received, it sits comfortably in the temperate zone. Models estimate the planet gets about 86% of the sunlight Earth receives. That's enough to support liquid water on the surface, at least in theory. But sunlight alone doesn't determine temperature. How that energy is distributed, retained, and cycled is equally critical. Greenhouse gases play the first and most obvious role. CO2, water vapor, methane, all these molecules trap heat in the atmosphere. On Earth, They keep the planet warm enough for life to thrive. On TOI-700d, their presence could mean the difference between a planet with frozen oceans and one with temperate regions. Scientists use computer models to simulate scenarios. A thin atmosphere with just enough CO2 could allow daytime temperatures to hover near the freezing point, while the terminator zone, the narrow twilight belt between the day side and night side, remains mild. Add more CO2, and heat circulates more efficiently, potentially keeping large areas of the day side warm enough for liquid water, while the night side remains frigid. The terminator line is where climate modeling becomes fascinating. TOI-700 days is likely tidally locked, with the same hemisphere facing the star constantly. That means one side experiences eternal noon, blazing under continuous sunlight, while the opposite side is in permanent darkness. Without atmospheric or oceanic circulation, the day side could overheat while the night side freezes solid. But simulations from NASA Goddard suggest that winds could transport heat around the planet, moving energy from the hot side to the cold side, moderating extremes. Clouds could form over the substellar point, reflecting some of the light and reducing surface temperatures. Oceans, if present, could act as massive heat reservoirs, redistributing warmth across the planet. This isn't speculation pulled from thin air. It's the same physics that drive Earth's climate, applied under a new set of conditions. Chemistry, not just heat, is key. Carbon dioxide cycles through the atmosphere, oceans, and crust. On Earth, volcanic outgassing releases CO2, while weathering removes it. TOI-700 days could host similar processes, though the details remain unknown. If it has active geology, the planet might maintain a balance, keeping temperatures in a habitable range over billions of years. If the cycles falter, CO2 could accumulate, triggering a runaway greenhouse effect like Venus, or deplete, plunging the world into a deep freeze. Minute chemical imbalances could determine whether this planet supports liquid water or becomes a dead world. Magnetic fields is another factor. A strong magnetic field shields the atmosphere from stellar winds and cosmic radiation. On Earth, the geomagnetic field protects life and prevents the gradual loss of gases to space. TOI-700 days could have a magnetic field generated by a molten core. If it's strong, the planet might retain its atmosphere for billions of years, giving water, clouds, and potentially life a chance to persist. If weak or absent, even the quiet red dwarf could gradually strip the atmosphere. Solar wind particles, though less intense than flares from a star like Proxima Centauri, would slowly erode the atmosphere over time, shrinking habitable regions or even eliminating them entirely. Rotation rate is another subtle but important factor. Tidal locking doesn't mean the planet is static. Some simulations suggest slight libration. Tiny oscillations in rotation could spread energy unevenly across the surface, producing microclimates. Even small variations in rotation can dramatically alter wind patterns, cloud formation, and the location of stable temperature zones. The combination of rotation, atmospheric thickness, and heat transport is what determines whether water remains liquid in pockets along the terminator or evaporates into an unstable atmosphere. When we imagine TOI-700d, it's tempting to picture a pale blue world like Earth orbiting a faint red sun. But in reality, it's more complex. Its star, a quiet red dwarf, bathes the planet in light that's very different from our sun. TOI-700 emits mostly infrared and red light, very little blue or ultraviolet. That changes everything about how the planet interacts with energy, its oceans, clouds, and even the potential for life. Let's start with the oceans. On Earth, sunlight penetrates water, driving circulation, heating the surface, and enabling photosynthesis. On TOI-700d, the peak of stellar radiation is shifted toward longer wavelengths. Water absorbs infrared light differently than visible light. The upper layers of the oceans may warm slowly, while heat penetrates less deeply. This creates a different kind of stratification. Warm surface layers over cooler depths, with potential impacts on ocean currents. The terminator zone, the thin band between eternal day and night, could have mild temperatures where shallow seas remain liquid, while the day side warms enough to support larger, more dynamic oceans, and the night side freezes partially. Clouds are the next factor. Water vapor condenses differently under red light because the thermal balance is shifted. On Earth, cloud formation depends on convection driven by solar heating and surface temperature differences. On TOI-700d, the infrared-rich light might create slower, more gradual convection patterns, producing extensive but stable cloud decks over the substellar point. These clouds act as regulators, reflecting some incoming energy and redistributing heat across the planet. In simulations, cloud cover can moderate the extremes between the day side and night side, preventing overheating while keeping parts of the terminator zone suitable for liquid water. The chemical composition of the oceans could also differ. On Earth, ocean chemistry is influenced by sunlight, volcanic activity, and the cycling of elements like carbon, nitrogen, and sulfur. TOI-700 days may have similar cycles, but the intensity and spectrum of light affect the rates of chemical reactions. For instance, infrared-rich light penetrates less deeply, so photochemistry in the upper layers could be weaker, potentially altering the formation of oxygen or ozone from water photolysis. Methane and other greenhouse gases might accumulate differently, depending on how sunlight drives chemical reactions in the atmosphere. This spectral shift also changes how potential life could function. On Earth, photosynthesis relies on visible light. Plants capture photons, using energy to split water molecules and generate carbohydrates. Under a red dwarf, visible light is limited, so if life exists on TOI-700d, it would need to rely on infrared photons. Infrared light carries less energy per photon, so organisms might need to capture more photons to perform the same chemical reactions. Evolution, if it occurred, might favor large, broad-surfaced organisms or structures optimized for low-energy light harvesting. Pigments could be tuned to absorb red and near-infrared light efficiently, creating landscapes that, if visible from space, might appear dark red or black rather than green. Photosynthesis under a red dwarf could also rely on alternative chemical pathways. On Earth, oxygenic photosynthesis produces oxygen as a byproduct. On TOI-700d, infrared-based photosynthesis might not release oxygen efficiently, leading to atmospheres with different compositions. Methane, ammonia, or other compounds could dominate as byproducts. That changes how we interpret potential biosignatures. Instruments like JWST would need to look for unusual gas combinations, ozone, methane, or carbon dioxide in ways not typical of Earth to assess habitability. The atmosphere itself interacts with the oceans and clouds in complex ways. A denser CO2-rich atmosphere can trap heat, preventing the night side from freezing completely. Conversely, a thinner atmosphere could allow temperatures to plummet on the dark side, creating permanent ice. Clouds might form in bands along the substellar point, reflecting heat, while winds transport moisture and energy toward the terminator. Oceans could serve as heat reservoirs, moving warm water toward the night side and moderating extremes. Each of these factors, atmosphere, clouds, oceans, is interdependent. Change one, and the climate shifts dramatically. One fascinating aspect of modeling TOI-700d is how heat is transported between the day and night sides. Unlike Earth, where the rotation spreads sunlight around the globe, tidal locking means one side constantly faces the star. Atmospheric winds and ocean currents become the only way to move energy. In the best-case scenarios, these processes maintain stable temperatures in the terminator zone, creating a ring around the planet where oceans remain liquid and climates are mild. This is where life would have the best chance to survive, assuming oceans exist and the atmosphere is dense enough to circulate heat. Chemistry in the clouds themselves could also be unusual. Water droplets may mix with CO2 or other compounds, creating acidic or alkaline clouds. This would impact precipitation patterns and the types of minerals dissolved in surface oceans. Rainfall could be intermittent and localized, depending on heat distribution and wind patterns. Chemical interactions between the atmosphere and surface would drive cycles similar to Earth's carbon or sulfur cycles, but under different energy and spectral conditions. Infrared light also affects surface temperatures in subtle ways. Because infrared penetrates clouds and atmosphere differently than visible light, surface heating may be uneven. Dayside regions directly under the substellar point could reach temperate or warm conditions, while nearby regions under cloud cover remain cooler. This patchiness could create microenvironments with differing chemical concentrations, salinity, and nutrient availability, all important for potential life. From a human perspective, it's tempting to speculate about habitability, but the reality is constrained. We don't know if TOI-700d has oceans, continents, or a magnetic field. We can model possibilities, but confirmation requires direct observation. JWST may detect atmospheric components, hinting at water vapor or CO2 levels, but it cannot confirm the existence of oceans or life. These are the limits of current technology. What we can do is simulate the chemistry, climate, and energy balance under the star's red light spectrum, giving us realistic scenarios for how this planet behaves. Chance remains a factor. The planet's formation history, how much water it retained during its early years, whether it experienced massive impacts, whether its core is molten, affects current conditions. A slight variation in initial water content or atmospheric composition could mean the difference between a world with liquid oceans and one that is frozen solid. Even with perfect modeling, there's uncertainty. This is a planet shaped by both physics and chance, by chemistry and history. The implications of red light photosynthesis are profound. Life, if it exists, would not look or behave like life on Earth. Energy capture would be slower, possibly favoring slow-growing or low-energy organisms. Pigments would absorb differently, possibly darkening the surface. Ecosystems would evolve under dimmer, longer wavelength light, with unique strategies to maximize energy. Oxygen might be less abundant, methane more common, and unusual atmospheric chemistry could dominate the spectra that telescopes detect. Clouds and oceans are critical moderators. Without them, the dayside could overheat, the nightside freeze, and the terminator zone could become the only habitable region, a narrow, fragile ring. With them, the planet could maintain broad areas suitable for liquid water. The interplay of chemistry, cloud formation, and heat transport is what makes TOI-700d so fascinating scientifically. It's a world in balance, a delicate system shaped by stellar spectrum, tidal locking, and chemical processes. Every factor from initial mass to stellar activity history interacts to determine habitability. On a planet like TOI-700d, science is only part of the story. The planet's past and the hand of chance shape its present. Simulations suggest several potential climates. One possibility is a world where the dayside hosts deserts or shallow seas, warm but not scorching. The nightside freezes over completely, perhaps with ice sheets extending halfway around the planet. Along the terminator, temperatures hover in a range where liquid water is stable, small seas, seasonal rainfall, and temperate conditions that might last for billions of years. In another scenario, a thicker atmosphere distributes heat evenly, making the dayside and nightside more similar. Temperatures might be moderate across most of the surface, with only minor extremes. Both outcomes depend on the interaction of chemistry, heat transport, and rotation. Magnetic protection could be the deciding factor between these scenarios. Even a quiet red dwarf produces low-level stellar wind, enough to erode the atmosphere over geological timescales if unshielded. A strong field, generated by a molten core, would defend against this erosion, stabilizing the climate and retaining the planet's gases. A weak field could allow gradual atmospheric escape, thinning the atmosphere, reducing greenhouse efficiency, and shrinking habitable zones. The chemistry also sets the stage for potential biosignatures. Ozone could form in an oxygen-rich atmosphere, methane might accumulate in regions where UV radiation is low, and water vapor signals could reveal stable oceans. Instruments like JWST could detect these signals from Earth, providing indirect evidence of habitability. TOI-700 days becomes a laboratory for understanding how chemical cycles operate on planets unlike Earth, yet similar enough that life might, in principle, survive. Another factor is stellar stability. TOI-700's quiet nature reduces radiation spikes, giving the planet's atmosphere a chance to stabilize. Without frequent flares, chemical cycles are less likely to be disrupted, magnetic shielding remains effective, and temperature regulation is more reliable. Compared to volatile stars, where flares can vaporize water or strip the atmosphere entirely, TOI-700D's environment is remarkably forgiving. It is not a guaranteed habitable world, but it is among the few where the odds are scientifically measurable. Chance continues to influence the outcome. Minor differences in axial tilt, atmospheric composition, or even planetary albedo, the reflectivity of the surface, can dramatically change climate. A slight difference in CO2 concentration or cloud density could shift temperature ranges by tens of degrees. In a system like TOI-700, these small variables might determine whether liquid water survives in the terminator zone or disappears entirely. Habitability is fragile, and on a world this distant, we can only simulate scenarios, refine models, and prepare for the day when instruments like Habitable, LUVOIR, and LIFE can confirm which scenarios actually exist. Instruments like JWST, Habitable, and LUVOIR give hope that these theories can be tested. Spectral measurements can detect water vapor, carbon dioxide, ozone, and methane. Observing absorption bands under red light conditions will help scientists validate climate models, estimate ocean stability, and refine understanding of photosynthetic possibilities. While life cannot be confirmed, habitability parameters can be measured, and this is a major leap forward. Why TOI-700 matters? Here's something that often gets lost in all the Earth 2.0 headlines. No one actually expects another Earth. TOI-700 days matters because it isn't Earth, but it still might be livable. Think about that. It orbits closer to its star than Mercury orbits our Sun, but the star is so dim that the planet still sits in the sweet spot. That flips our whole picture of habitability on its head. It tells scientists that distance from the star doesn't define habitability anymore. Context does. Star type, atmosphere, rotation, magnetic field, those things decide whether a planet can keep water or life, not just how far away it is. TOI-700 days forced astronomers to rethink the basics. It became a real-world test case for what we used to think only existed in simulations. In astrobiology, the study of life in the universe, every discovery is like a new clue in a mystery we've been trying to solve forever. TOI-700 days gave scientists something priceless, a nearby target that's actually reachable for study. Not for travel, obviously. It's still about 100 light-years away, but reachable for telescopes like JWST and soon LUVOIR and Habitable. It's a perfect target for atmosphere scanning, the kind where you look for gases like oxygen, methane, and carbon dioxide, the chemical fingerprints that hint at life or geological activity. If we detect something unusual there, it would tell us two things. Life doesn't need a sun-like star to exist. Second, we've been too narrow-minded about where to look. It's not proof of aliens. It's proof that life might adapt to more environments than we ever imagined. That's why TOI-700D is now part of a short list of priority worlds for biosignature studies. The kind of list NASA builds when it wants to focus resources on targets that can actually change our understanding of life itself. TOI-700 days isn't just interesting on its own, it's a template. When TESS found it, it showed how small, cool stars could still host stable, rocky worlds. That's huge for future surveys. Why? Because those stars are everywhere. They're dimmer, easier to block out in transit detection, and their planets pass in front of them more often. That means the next generation of telescopes can use the TOI-700 system as a reference, a model of what quiet red dwarf habitability looks like. It's also teaching scientists how to spot false positives, how to measure faint atmospheres, and how to tell if what we're seeing is real or just data noise. Every method refined here, from light curve analysis to spectral fingerprinting, makes us better at catching the next one. That's why TOI-700d is often called a Rosetta Stone for red dwarf planets. It's the benchmark that helps decode others. The discovery also shook up ideas about how planets form around small stars. Red dwarfs were once thought to form mostly small, dry, rocky worlds, the kind that lose their atmospheres fast. But TOI-700d's stable orbit and likely thick atmosphere suggests something else. Maybe planets around these stars can hold on to gases and oceans for billions of years after all. Maybe the process of planetary formation is more diverse than we thought. Scientists used to think you needed a big, warm, sun-like star to get an Earth-type planet. Now, TOI-700d proves you don't. That doesn't just change how we look for planets, it changes how we understand where we came from. It shows us that Earth might not be the special exception we once thought it was. This is where things get exciting for regular people, not just scientists. Because for decades, books and movies imagined red sky worlds orbiting tiny stars, places that felt alien but still strangely possible. For a long time, those were pure fiction. Then, TOI-700d showed up. Suddenly, the science fiction image of a dim, reddish world with long days and strange horizons wasn't just imagination anymore. It was a real-world example. It's one thing to dream about another habitable world. It's another to see one in the data, to know it's there. So what could actually be happening down there? What kind of world are we talking about? Let's be honest, we don't know yet. But here's what we can piece together. If TOI-700d has an atmosphere, and there's good reason to think it might, then the surface could be surprisingly mild. Models suggest an average temperature near what we'd feel in Earth's polar regions. Cold, but survivable with the right conditions. If it's tidally locked, one side would always face the star, bathing in constant reddish daylight, while the other side would sit in permanent night. The real question is whether heat can move between the two, whether winds or oceans can carry energy around the planet to balance things out. If that happens, you might get a world where the twilight zone, the line between day and night, is the most habitable region. A band of perpetual sunset running around the planet. A place where life, if it ever appeared, could thrive in stable, moderate temperatures. It's not a guarantee, but it's possible. And that's what keeps astronomers hooked. Let's talk about the star again for a second, because this is where the real significance hides. For years, the big problem with red dwarfs was their behavior. They're small, yes, but they're unstable. They flare up, release bursts of radiation, and can easily strip the air off their planets. TOI-700 doesn't do that much. It's one of the calmest red dwarfs observed so far. That means its planets might have kept their atmospheres for billions of years, enough time for chemistry, for oceans, for maybe even biology to evolve. Every time we find a world like TOI-700d, the universe feels a little smaller and a lot more familiar. This discovery tells us that planets like ours aren't rare accidents. They might be standard issue. That means life might not be some miracle event unique to Earth. It might be a natural outcome of how galaxies work. That doesn't make Earth any less special. It makes the universe more alive. TOI-700 days matters because it reminds us that our story might not be the only one. Somewhere out there, under a dim red sun, another world might be waiting. Quiet, cold, maybe even empty for now, but full of possibility. And that's where we are right now, caught between what we know and what we can only guess. The future of habitable planet hunting. The truth is, TOI-700d didn't just give us a new world, it gave us a new reason to keep looking. Before its discovery, exoplanet hunting already felt like a race, but this one changed the pace. Every discovery from here on out will build on what TOI-700d taught us, that habitable worlds can hide around small, dim stars that were once written off as too unpredictable. That's why the next phase of exploration feels different. It's not guesswork anymore. We know what to look for, where to look, and how to measure it. And that's exactly where the future observatories come in. The James Webb Space Telescope was the first taste of this new era. It can already pick apart the faintest hints of atmospheres, separating molecules of carbon dioxide or methane from the light of distant stars. But Webb was never meant to do it all. It's the bridge, the one that opens the door for what's coming next. The next generation of observatories, Habex, Louvois, and Life, are designed for one goal: to actually see these worlds. Not infer them, not model them, see them. That's what makes this era revolutionary. Because for the first time, scientists aren't chasing shadows, they're preparing to capture the real thing. Habex, short for the Habitable Exoplanet Observatory, is being designed to search for Earth-like planets around nearby stars with a clarity no telescope has ever achieved. It's built around a simple idea: block out the star's light so you can finally see the faint glow of a planet beside it. To do that, it uses something called a starshade, a massive flower-shaped screen that would fly tens of thousands of kilometers in front of the telescope, perfectly aligned to cancel out starlight. If it works, it will reveal the planet next to it like a speck of dust in the dark. Louvois, on the other hand, will be even bigger. A space telescope so powerful, it would make Hubble look like a toy. Its mirrors could stretch over 15 meters wide, giving it the sensitivity to spot faint planets and analyze their atmospheres in detail. Louvois isn't just about discovery, it's about context. It will let scientists compare multiple planets at once, the kind of analysis that turns a list of dots into a real understanding of how planetary systems work. Then there's Life, the Large Interferometer for exoplanets. This one is wild. It's a concept for several spacecraft flying in formation, combining their light data like one massive telescope. With that setup, scientists could directly detect the heat coming off planets, even measure their temperature, cloud patterns, and potentially signs of chemical imbalance that might hint at biological activity. All three of these missions have one shared goal: direct imaging. That's the Holy Grail. Because once you can see a planet directly, you can study it in ways we've only dreamed about. You can measure its brightness, color, even the way light scatters in its atmosphere. You can tell if there are clouds, oceans, or continents. You can spot seasonal changes. You can see if the planet breathes. And that's where things get real. Because when you can actually see a blue dot orbiting a red star, it stops being an abstract target. It becomes a place, a world. You see, the idea of life is almost too big to chase directly. We can't recognize alien biology we've never seen, but we can recognize the conditions that make life possible: the right temperature, the right chemistry, the right protection. That's what makes TOI-700D and future targets so important. They help define the parameters of potential. Scientists want to know whether a planet's air stays thick enough to trap warmth, whether its surface could keep liquid water stable, whether its star gives steady light or violent bursts, whether gravity and rotation balance in a way that keeps the climate in check. If those conditions align, you don't have proof of life, but you have the right recipe for it. And that's the foundation every future mission is built on. The next few decades will be about testing that recipe on as many planets as possible. Webb is already collecting early results. Future missions will refine them. Each new observation will narrow the list of real contenders. Worlds that don't just exist, but could genuinely host something alive. The exciting part is that this shift isn't just about distant space. It changes how we see ourselves. Every time we discover a potentially habitable world, it forces us to ask what habitable even means. Does it mean Earth-like? Or does it mean possible in another form? Could a planet with thick carbon dioxide clouds still support microbial life? Could an atmosphere tinted in methane or ammonia be a sign of alien chemistry instead of toxicity? These questions used to sound hypothetical. Now they're part of real data analysis. The future of habitable planet hunting isn't about chasing the familiar anymore, but expanding the definition of possible. We're learning that the universe doesn't need to copy Earth to create life-friendly conditions. It just needs balance, The right mix of energy, chemistry, and time. And with red dwarfs being the most common stars in the galaxy, that balance might appear in places we've ignored until now. That's what TOI-700d started. It gave credibility to a whole new class of planets. Smaller, dimmer, longer living systems where life could quietly evolve under red light instead of yellow. Habex and Louvois will make that exploration visual. They'll give us snapshots of these systems and let us study them not as data points, but as environments. Scientists will be able to compare one red dwarf world to another, track how their atmospheres react to flares, or see how clouds shift over time. Each discovery will add another layer to our understanding, another puzzle piece in figuring out how common truly habitable planets are. And it's not just NASA, the European Space Agency, private companies, and even independent researchers are all getting involved. We're heading toward a future where space exploration is no longer limited to one organization or one country. It's becoming a global effort, a shared mission to answer a shared question. What's fascinating is how this hunt blends deep science with raw curiosity. The technology behind these telescopes is advanced beyond anything we've used before. Precision optics, formation flying, adaptive mirrors, and algorithms that can isolate a single photon from a billion. But at the core of it all, it's still the same human drive, the need to know if we're alone. When Louvois or life eventually locks onto a planet and captures that first direct image, it will be one of those moments that divides history into before and after. Before, we knew only through shadows. After, we've seen it with our own eyes. That image, a small glowing dot orbiting a dim red star, might not look impressive to most people, but for science, it will be everything. Because from that single pixel, we'll be able to tell whether the atmosphere is stable, whether clouds scatter light like Earth's, and whether the color hints at oceans or vegetation. It's the kind of moment that could change how humanity thinks about itself. That's why the search for habitable planets is no longer just an academic exercise. It's a turning point for civilization. It's the step where exploration shifts from mapping space to understanding life beyond it. And TOI-700d stands right at that threshold, the bridge between what we found and what we're about to see. It proved that quiet red dwarfs can host stable planets. It gave scientists a nearby target that's scientifically rich and physically reachable for observation. It set the standard for what we call the next frontier. When people think about future telescopes, they often imagine the hardware, the mirrors, the detectors, the spacecraft. But what really drives it all is the question, the same one that started when we looked up thousands of years ago and wondered what those lights were. Now we know some of them are suns, some of them have planets, and some of those planets might be capable of life. The tools are just extensions of that wonder. Every improvement in technology gets us closer to uncovering another layer of the unknown. Every clearer image gives us another reason to believe we're close. It's not about proving life exists somewhere else. It's about not assuming it doesn't. That's the mindset driving this new generation of missions. Cautious optimism backed by data. No hype, no fantasy, just progress. And progress is exactly what's happening. The pace of discovery is accelerating fast. 20 years ago, we didn't know of a single exoplanet like Earth. Now, there are thousands of candidates and dozens of confirmed rocky worlds in habitable zones. TOI. 700 days just happens to be one of the most promising, but it won't be the last. The more we look, the more patterns we'll find, and patterns mean predictability. Once we can predict where habitable planets should form, we can target them efficiently, collect better data, and maybe even catch early signs of biosignature gases in their atmospheres. At that point, we'll no longer be wondering if life might exist elsewhere. We'll be investigating where it likely already does. That's what this era of observatories is about. It's not just looking for another Earth. It's preparing to recognize the unfamiliar, to understand life that might not look anything like ours. That's the real legacy of TOI-700d and the telescopes that will follow. They're not chasing myths. They're building a new reality. A reality where seeing a habitable world around another star isn't breaking news. It's normal. And when that day comes, when the first true Earth-sized planet with an oxygen atmosphere and surface oceans is confirmed, the entire story of science will shift. The question of whether we're alone will finally have a data-driven answer. Not just belief, not just hope, but evidence. The numbers behind the stars. Before telescopes could catch the faint heartbeat of a distant planet, astronomers had no way to count Earth-like worlds. There was no data, only math, and one bold equation that tried to make sense of what we couldn't yet see. In 1961, a radio astronomer named Frank Drake gathered a small group of scientists in Greenbank, West Virginia. Their goal was to talk about the search for extraterrestrial life, but to do that, Drake realized they needed a framework, a way to turn a mystery into a number. On a chalkboard, he wrote an equation that broke down the odds of intelligent life into parts: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the odds of life starting, of intelligence forming, and of civilization surviving long enough to be detected. At the time, most of those numbers were wild guesses. No one even knew if planets were common. The first confirmed exoplanet wouldn't be discovered for another 30 years. Still, the Drake equation gave scientists something powerful, a way to think about life in the universe using science instead of speculation. For a long time, the equation sat between fact and imagination. Each term was an empty box waiting for data. Then telescopes like Kepler and TESS came online, and suddenly we weren't guessing anymore. When NASA launched the Kepler Space Telescope in 2009, it changed everything. Kepler stared at over 150,000 stars, tracking tiny dips in brightness that meant a planet was crossing in front. The result was staggering. Thousands of confirmed worlds, most of them smaller than Neptune, many the size of Earth. For the first time, astronomers could look at an actual sample of planets and start calculating probabilities. That's where eta Earth comes in. It represents one part of the Drake equation, the fraction of stars that have planets roughly Earth-sized in the habitable zone, where liquid water could exist. Early estimates were cautious, but as more data rolled in, the numbers began to settle. Depending on how you define Earth-like, the fraction could be as high as 1 in 5. That means for every 5 sun-like stars, one might have a planet roughly the size of Earth, receiving similar levels of light. Considering there are over 200 billion stars in our galaxy, that's tens of billions of potential Earths. Even red dwarfs, smaller and cooler than our Sun, turned out to be fertile ground. Kepler showed that rocky planets are more common around these dim stars than anyone expected. Since red dwarfs make up nearly 70% of the Milky Way, that discovery reshaped our sense of probability. Instead of wondering if there might be another Earth, astronomers began asking how many hundreds or thousands might already be out there. When Drake first wrote his equation, it was like filling in a crossword puzzle with no clues. Today, we've solved the first few squares: the rate of star formation. Roughly 1 or 2 new stars are born in our galaxy each year. The fraction of those stars with planets? Almost every star has them. Kepler and TESS made that clear. The days of thinking our solar system was rare are over. Next comes E, the heart of habitability. This is where things get both exciting and messy. Astronomers use different definitions for Earth-like. Some count any rocky planet within the star's habitable zone, even if it's twice Earth's mass or gets a bit more radiation. Others only count those with similar size, orbit, and energy input. Depending on which criteria you use, E could range anywhere from 0.1 to 0.5, meaning 10 to 50% of stars may have at least one potentially habitable planet. But raw numbers don't tell the full story. The challenge lies in observation limits. We can only detect planets that happen to pass in front of their star from our point of view, a rare alignment. For every world we see, there are many we miss. Astronomers use statistical corrections to account for that, running millions of simulated planetary systems to see how often we'd catch a transit. It's not perfect, but it gets us close. This kind of statistical modeling is how scientists moved the Drake equation from theory into something testable. Instead of asking, how likely is life? They now ask, how likely is a world that could support life? Today, when scientists revisit the Drake equation, they plug in real data for the first few terms. Star formation rate, known. Fraction of stars with planets, close to 1. Fraction with Earth-sized planets in the habitable zone, roughly 1 in 5. The remaining factors, life, intelligence, and communication, remain uncertain, but we're not operating in the dark anymore. The shift is profound. What used to be philosophical is now statistical. Astronomers can estimate that our galaxy alone might hold 20 billion potentially habitable worlds. Even if just a fraction of those ever develop life, the odds are no longer cosmic fantasy. They're measurable. It's important to note that habitable doesn't mean inhabited. A planet might sit in the right zone for liquid water, but without an atmosphere, magnetic field, or stable rotation, it could be barren. That's why missions like JWST and the upcoming Habitable Worlds Observatory matter so much. They're not just finding planets, they're analyzing their skies. By studying the light that filters through a planet's atmosphere during a transit, astronomers can detect gases like carbon dioxide, methane, and oxygen, chemical fingerprints of potential life. When those telescopes feed that data back into the Drake framework, the next term, the fraction of habitable planets that actually develop life, can finally move from unknown to measurable. E is one of the most debated numbers in modern astronomy. Some teams, using Kepler's final dataset, suggest it could be around 0.24 for Sun-like stars, about 1 in 4. Others, using conservative criteria, place it closer to 0.1. For M-dwarfs, it might be even higher. Studies of systems like TRAPPIST-1, LHS 1140, and TOI-700 suggest that small cool stars commonly host multiple Earth-sized worlds in the habitable zone. That means if you point your telescope at any red dwarf in the night sky, there's a good chance at least one of its planets could be temperate and rocky. Not every one of those will be friendly to life, but the odds stack up quickly when you multiply by the sheer number of stars. To get to these numbers, scientists run massive simulations. They take the thousands of real exoplanets we've already found, then model billions more to fill in the observational gaps. They test how detection biases skew the data, account for flare activity that might strip atmospheres, and simulate the chemical evolution of planetary surfaces under different star types. It's not guesswork anymore. It's evidence-based extrapolation. Every new planet we discover helps refine E, making the equation sharper. Imagine the Milky Way stretched out before you, a disk of stars spanning 100,000 light-years. Now imagine marking a single dot for every potentially habitable planet. You wouldn't see dots here and there. You'd see a haze of light, a galaxy speckled with billions of possibilities. That visualization is what keeps exoplanet scientists going. Each discovery pushes the statistics higher, confirming that our solar system isn't an outlier. It's one of many variations on a common theme. Even more revealing are the planetary systems that challenge our assumptions. Systems like TOI-700 or TRAPPIST-1 show multiple Earth-sized planets packed closer than Mercury is to our Sun, yet stable and enduring. That kind of efficiency, so many potentially habitable worlds around one small star, raises E not just per star, but per system. If those systems are typical, then the galaxy could hold more habitable real estate than we ever imagined. The next frontier isn't about discovering more planets, it's about knowing what they're made of. We're entering the phase where exoplanet data feeds directly into habitability models. JWST has already observed the atmosphere of a super-Earth called 55 Cancri e, and though that world is far too hot for life, the same techniques can be applied to cooler, Earth-sized planets. By analyzing atmospheric spectra, astronomers can tell if a world has greenhouse gases, water vapor, or hazes that block starlight. Each of those clues narrows the range for E. refining which planets are truly Earth-like in chemistry, not just size or orbit. Future missions like the Habitable Worlds Observatory and Le Voir, if funded, will push even further, directly imaging exoplanets instead of relying on transits. Once that happens, we'll move from probability to confirmation. Instead of saying 1 in 5, we'll be able to count them, not by equation, but by image. What's happening now is a transformation in how we approach the question of life beyond Earth. The Drake equation used to be a way of organizing uncertainty. Now, it's becoming a framework for measurable science. We've filled in the early terms, and each new telescope will chip away at the rest. As we refine E and other parameters, something subtle but powerful happens. The conversation moves away from, is life possible, toward, where should we look next? That's the mark of progress, turning the abstract into action. We're no longer waiting for evidence of another Earth. We're building the instruments to find it. The fact that we can even estimate E with confidence shows how far astronomy has come since Frank Drake's chalkboard equation. The Drake equation is a roadmap. Each telescope, each observation, each line of data fills in a blank that once belonged to imagination. We now know that nearly every star has planets. Many have rocky ones. A significant fraction of those lie in zones where water could exist. Those are measurable facts. What remains uncertain, life itself, is shrinking behind a wall of growing evidence. With each new world catalogued, with every spectrum captured, the probabilities tighten. When Drake first drew that equation, he couldn't have imagined we'd one day be counting Earth-like worlds by the dozens, soon by the hundreds. But here we are, living in the age he only dreamed about. We can't yet say how many of those worlds host life, but for the first time, we can count how many worlds like ours might really exist. The chemical signatures of life. When Earth is viewed from space, its spectrum stands out. There's oxygen in the air, methane produced by microbes and agriculture, and water vapor drifting across the surface. Those gases shouldn't coexist for long without something constantly replenishing them. In our case, life. That mix is called a biosignature, and it's what astronomers are looking for on exoplanets. But it's not simple. A single molecule can be misleading. Volcanoes can release methane. Ultraviolet radiation can split water molecules into oxygen. A planet can mimic life without hosting it. So scientists look for combinations, atmospheric balances that make sense only if biology is involved. One of the strongest indicators would be finding oxygen and methane together. On Earth, those gases destroy each other quickly, so their coexistence means something must be continually producing both. Detecting that same imbalance on another planet could be the first real sign of alien metabolism. But to catch that signal, we need precision instruments that can isolate faint spectra from the glare of a distant star. That's where the James Webb Space Telescope changed the game. When a planet crosses in front of its star, a fraction of the starlight passes through the planet's atmosphere before reaching us. Different gases absorb light at specific wavelengths, carving tiny gaps in the star's spectrum. JWST measures those gaps. By spreading that light into its component colors, it builds a chemical profile of the atmosphere. For gas giants, this method works beautifully. Their thick atmospheres block more light, making them easier to study. For Earth-sized worlds, it's far harder. The signal is tiny, often less than a few parts per million. That's why scientists observe multiple transits, stacking the data to increase clarity. JWST's first results have already proven the concept. It detected carbon dioxide on the exoplanet WASP-39b and water vapor on several others. None of those worlds are habitable, but the success shows the system works. The next step is to apply it to cooler, rocky planets like TRAPPIST-1e or TOI-700d. Only a handful of exoplanets are close and quiet enough for atmospheric study right now. Red dwarf systems are ideal targets because their stars are smaller and dimmer, meaning a planet blocks more of the star's light during transit. That makes atmospheric signals stronger. Planets like TOI-700d and LHS 1140b are high on that list. They're close enough for follow-up observations, and their stars are relatively stable. For astronomers, that's crucial. A single flare from a red dwarf can drown out the faint spectral fingerprint they're trying to measure. Future missions will expand this list dramatically. The European Space Agency's Ariel mission, launching later this decade, will analyze the atmospheres of hundreds of exoplanets. While it won't detect life directly, it will map chemical patterns across planetary types, a database that will tell us where to look deeper. While atmospheric chemistry focuses on biology, there's another frontier: technology. A technosignature is any detectable evidence of technology on another world. Artificial light, radio signals, industrial gases, or even satellite swarms. The idea may sound speculative, but it's rooted in physics. If a civilization developed like ours, it might alter its planet's atmosphere. On Earth, for example, chlorofluorocarbons, CFCs, didn't exist before the 20th century. They're purely synthetic. Detecting similar compounds elsewhere would be hard to explain as natural. SETI scientists are now combining traditional radio searches with optical and infrared methods. Instead of waiting for deliberate signals, they're looking for side effects, light patterns or energy imbalances that could result from large-scale technology. A reflective megastructure orbiting a star, for instance, would cause irregular dips in brightness. Something similar was seen with the now famous Tabby's star. It turned out to be dust, but the search techniques it inspired are being refined and reused on newer targets. Astronomers often use Earth as a baseline. If we were observing our own planet from 100 light-years away, what would we see? We'd see seasonal changes in atmospheric gases. We'd notice oxygen levels rise and fall as plants grow and die back. We'd see reflected light shift slightly, with cloud patterns and ocean glints. Those small variations would reveal that Earth isn't static. It's dynamic, alive. That's what scientists are now trying to detect elsewhere. Using time series observations, they track how a planet's light changes as it orbits. A consistent seasonal pattern could point to weather cycles or even photosynthetic processes. On red dwarf planets like TOI-700d, that pattern would look different. The light is redder, the seasons might be shorter, and the climate could be locked between permanent day and night sides. If life exists there, its chemistry might adapt to infrared light, pigments that capture longer wavelengths, similar to how some Earth bacteria thrive in deep, dim water. Detecting that kind of biochemistry won't be easy, but instruments are getting close. The proposed Large Interferometer for Exoplanets mission would combine light from multiple space telescopes to directly image small exoplanets and analyze their thermal spectra. It's still in concept stage, but its goal is simple: to see life's chemistry from light years away. Even when we detect something that looks like a biosignature, the work doesn't end. It's just the beginning. Every candidate signal must survive an intense process of elimination. Could volcanism explain it? Could the star's radiation split molecules in a way that mimics biology? Could instrument noise or calibration errors create false positives? To confirm a true biosignature, astronomers need redundancy, multiple detections of the same signal across independent instruments, and supporting evidence like stable atmospheric composition or surface temperature estimates consistent with liquid water. That's why exoplanet science is slow, cautious, and meticulous. The field remembers the lessons of past excitement, like the 1996 Mars meteorite announcement that turned out not to be evidence of life after all. The goal now isn't to rush discovery, but to prove it beyond doubt. When that day comes, when we finally detect a stable, repeatable biosignature, it won't be treated as a headline. It'll be treated as data, verified, cross-checked, and then published as fact. The most valuable part of studying exoplanet atmospheres isn't just finding one world that looks like Earth, it's comparing hundreds. Once we have a catalogue of atmospheres, patterns begin to emerge: how temperature, star type, and planet size influence chemistry. For instance, super-Earths often retain thicker atmospheres, rich in hydrogen and helium, while smaller, cooler planets show signs of water vapor and carbon dioxide. That contrast helps define the boundary between sterile and potentially life-friendly worlds. Over time, this database will become the foundation for astrobiology, a statistical understanding of what conditions lead to stable, long-term habitability. It's no longer about finding a twin Earth. It's about finding the range of possibilities. Within the next decade, several new observatories will come online that will redefine our reach. NASA's proposed Habitable Worlds Observatory aims to directly image Earth-like planets around Sun-like stars, something no telescope has ever done. It'll use advanced coronagraphs to block starlight and expose the faint glow of the planets themselves. ESA's LIFE mission will go even further, using interferometry to detect mid-infrared light where thermal emissions carry information about surface temperature and atmospheric composition. These missions, working in tandem with JWST and Ariel, will create a multi-layered approach, one focusing on visible light, another on infrared, and another on thermal emission. For the first time, we have the instruments to test one of science's oldest questions using direct observation. We're not waiting for aliens to call, we're studying their skies. Every new detection, even a non-biological one, sharpens our understanding. A barren world teaches us as much as a habitable one. Together, they draw the line between what's possible and what's not. By the mid-2030s, TESS, atmospheric spectroscopy will likely detect the first candidate biosignature, not a message from space, but a quiet signal buried in the light of a distant sun. It might be a hint of oxygen, a trace of methane, or an unexpected combination of gases that resists chemical explanation.